Good. Can people hear me on Zoom?
Yes, we can.
Okay. Video on. Okay, good. Okay, shall we get started? Cool. I think we're already almost in the middle of the semester. Lecture 11 number gives a hint about that. And we've covered a lot. Today we're going to cover memory controllers and hopefully simulation also. This is going to be a broad introduction to memory controllers. Even though we've been talking a lot about memory controllers, we never discussed them in a little bit more, let's say, depth as to what they do and how complicated they can be. We're going to cover that, and we're going to talk about some, let's say, future ideas on potentially making memory controller design simpler as well as higher performance. We're going to talk about using reinforcement learning to actually make decisions in the memory controller, which actually is a very interesting direction for, in general, designing systems and architectures. Somehow they should be making decisions on their own as opposed to making decisions that are dictated by humans at design time. So we're going to motivate that also. And then we're going to talk about simulation, which is going to be hopefully a fun lecture because you've been doing simulation in your labs. We're going to be doing more simulation, and we'll discuss some interesting things in simulation. So let's get started. So basically, all memory needs to be controlled in the end. We've been talking about in-memory computation. In-memory computation needs to be controlled also, but we're not going to talk about in-memory computation. Assume that memory is a device that gives you data when you access it. You need to control it, essentially. And that's what the function of a memory controller is, one of the functions, I should say. And all long latency memories have similar characteristics that need to be controlled in somewhat similar manners. In this lecture, we're going to focus on DRAM again. But as I said, many of the things that we have been discussing in this course are applicable to other memory technologies also. We just need to think a little bit differently and consider the constraints of other technologies. I'll give you an example in the next slide, actually. So it could be flash memory. It could be other emerging memory technologies, which we're going to cover hopefully tomorrow. We'll see how far along we get. But there are many interesting emerging memory technologies. And essentially, some of these technologies place other demands on the controller as well. So let's take a look at one example. This is a high-level overview of what a flash controller, SSD controller, looks like. And you can see that there's similarities to memory DRAM controllers, but they do a lot more than DRAM controllers today. So they do some refreshing, for example. That's part of what DRAM controller does, but they do refresh in a very different manner in SSDs because it's not at the same granularity, at the same time scale as DRAM controllers, because flash memory is supposed to be non-volatile, and it's not supposed to be refreshed actually, because it's non-volatile, right? It should not lose the data, but because of aging-related effects, it starts losing data relatively quickly, especially when the cells get older and you wear them out. As a result, after some point in the lifetime of flash cells, you need to refresh. You need to start refreshing them. So this controller does that refresh at a time scale that's much larger than milliseconds. It could be the time scale should be a month. Refresh every month, for example. Refresh every week. Refresh every day. But you can see that there is some similarity, right? But there also similarity. There's other similarity. You can use error correcting codes to fix random errors. But these error correcting codes are actually very complex in flash memory, as we discussed earlier. This memory is fundamentally very unreliable when you manufacture it. There are many, many errors that you get. And these error correcting codes actually fix those errors. And also they fix the errors that may happen during operation in the field as well, because these errors increase as the flash memory wears out. One of the characteristics of flash memory is it wears out. Whenever you write to a cell, you actually degrade the quality of the cell, meaning you store, you're not able to write to a cell more than some number of times, because after some point in time, the cell stops working, let's say. That's an abstraction level. There are multiple reasons why it stops working, but it stops working essentially. So it degrades over time as you keep writing to cells. So you need to manage that as well. So this doesn't exist in DRAM, at least as far as we are concerned so far. Maybe it exists at very long time scales. In that sense, no one takes that into account. But in flash memory, it exists in real time scales. For example, in some state-of-the-art flash memory, if you do 100 writes to a cell, the cell cannot store data. Of course, there's a distribution, but 100 is not a terrible number, right, Rakesh? And especially flash memory cells that can store many bits per cell. So we may actually have flash memory lectures later on. We'll see. But this is something that the memory controller here in flash memory needs to take into account. So what do? They try to do variable leveling. They try to ensure that none of these flash memory rows wear out in a disproportionate way compared to other flash memory rows. So they try to level the wear or level the writes across all of the flash memory rows. Everything fails at the same time, hopefully. That basically makes things more manageable, let's say. So they actually do variable leveling somewhere over here, which is not shown over here. They do other things like voltage optimization, garbage collection, page remapping. I'm not going to talk about those, but maybe we'll have a flash memory lecture. I will mention that also later on. So to do variable leveling, for example, you need to do page remapping, right? If you want to do variable leveling, that means that you do not want to write to a physical page more than you write to some other physical page, which means that you need to redirect the writes somewhere else so that you basically equalize the number of writes that are happening to different pages. How do you redirect the writes in a controller level? Well, you have a remapping table that remaps the page IDs that are coming from the host, which is the processor essentially, to physical page IDs. And you basically try to shuffle them using some algorithm. There are many variable leveling algorithms that people have developed for SSDs today. So that's an example that doesn't exist in the area, right? But this complicates the flash memory controller. So it's actually fascinating what goes on in here, but we're not going to talk about that right now. So this is another view, a better picture of the flash SSD controller. And interestingly, there's also a DRAM inside the SSD controller today that was not shown here in the previous picture, I think. Maybe it was shown. Yeah, it was not shown fully, but it's the buffer manager essentially. But basically you have DRAM over here to actually reduce the number of writes that go to the flash memory, because writes are bad, right? If you do writes directly to the flash chip, you actually wear out the flash chip. So why not have some memory that doesn't wear out inside the SSD controller so that you can manage those writes in a nice way? There are also other issues with writes. Writes can actually take a long time because you may need to remap the pages, etc. They cause garbage collection, etc. So we don't go into those, but you can read this paper that I mentioned multiple times in this lecture, actually, if you're really interested in what goes on in a flash memory controller. And that's the paper, basically. So we may have a lecture, as I said, talking about SSD controllers. And I have shown you the slide before. There are many, aside from this error mechanism, which is wear out, there are many other, also called program erase cycling in flash terminology, if you will. There are other errors that happen, read disturb errors we briefly discussed. And there are many mitigation mechanisms that people have developed. And existing flash memory controllers actually employ all of these today. Okay, so you can read more about it. I'm going to mention this in the simulation lecture briefly, but there's a lot of work in this area. And there's a lecture, this is a past incarnation of this course. And we have a special course on flash memory and SSDs that Mohammed and Rakesh have been leading. So if you're interested, you can ask questions to them on flash memory and SSDs. Or you can take the course if you are interested. Okay, so that's an example. And that's a much more complicated example, I would say, than DRAM. But we will see DRAM is already quite complicated. And DRAM also has many types. So let's discuss the DRAM types. We've discussed this briefly in past lectures, but DRAM has many different types with different interfaces optimized for different purposes, especially today. Today, we've seen a proliferation of DRAM, and a lot of DRAM types have actually gained a lot of traction because different workloads and different systems are being customized. For example, mobile phones have been driving low power DRAM. These devices also have been driving low power DRAM. Other systems are driving high bandwidth DRAM, like GPUs, right? So basically I'm talking about, there's also commodity DRAM that has been designed for general purpose systems, but there's low power DRAM, as I said, usually graphics systems, require high bandwidth DRAM. We talked about low latency DRAM that exists at high cost today, but very latency critical workloads can make use of that, like very high, very low latency packet switching engines that are employed in routers that are really on the critical path of internet traffic employ this sort of DRAM. 3D stacked DRAM usually provides high performance, like high bandwidth. So that's why GPUs have been increasingly using it, HBM. And there's more that you can read about and we've seen earlier. So the key is underlying microarchitecture of DRAM is actually fundamentally the same in many of these technologies. There are some architectural decisions that people make, which we have also covered briefly in an earlier lecture. I will also mention that in a couple of slides again. But underlying like the subarray architecture and then the bank architecture is essentially the same. What is different is some of the higher level decisions based on that underlying microarchitecture and certainly the interface. And if you can think of that, if this is the case, a flexible memory controller can support various DRAM types. And this is true, but this is really very difficult to do in practice because you need to design many different controllers to actually take into account the different timing parameters, for example, and different specifications of different memories. And this complicates the memory controller. So it's difficult to support all types and potentially upgrades. And what's really a killer for this is really analog interface is very different across these memories. Basically, if you look at DDR, GDDR, LPDDR, high bandwidth memory, the analog interface is completely different. So there's signaling, for example, low power signaling employed in low power DRAM. There's high bandwidth signaling employed in GDDR5, and certainly a very different kind of analog interface employed in high bandwidth memory. So if you want to, let's say, design a system that supports many controllers, you're basically amplifying your design effort as well as area. This analog interface actually costs a lot of area. So you can now see that we have many different DRAM types, and you're kind of constrained in terms of what you can include in a chip without significantly increasing the cost. So this is based on a paper that we're going to discuss actually in the next lecture in simulation. This is a DRAM simulator that we have developed. We've publicly released in 2015. This is actually heavily used in academia and industry for both research and development purposes. Of course, people modify it for their benefit. That's the beauty of simulation, as we will discuss. But you can see that at the time we released this simulator, there were a lot of DRAM types, even at that time. Today, actually, this have increased significantly. And there are many academic proposals, some of which we have seen in the past lectures. And we're going to mention some of those also. So basically, these are real. And this is going to probably continue to be, let's say, even more heterogeneous in the future, because as we specialize the systems for applications, which is a common trend that we have seen, we need to specialize the memory somewhat also. And that's basically what you're seeing in real industry as well. They're specializing the memory somewhat to the application domains that are going to use that memory. Maybe not completely, because underlying microarchitecture is essentially the same. They're just changing the interface, right? I would say maybe they're specializing to the use cases, right? High bandwidth, low power, general purpose. And these are actually 3D stacked actually has both high bandwidth as well as low power. That's why it's kind of its own category over here. Okay, so you've seen this slide before, and we've covered some of the differences between these technologies. I mean, you don't need to know anything really specific, but you know the general areas right now: high bandwidth, low power, etc. But you can read this paper that we had actually discussed if you really want to understand the differences between these technologies. I'm going to mention that later on again. Okay, this is the emulator. And this is the paper that we had discussed earlier to motivate latency, right? This paper examines different DRAM types and how do they affect different workloads. And there's a detailed discussion on the different DRAM types here. Any questions? It's just a backdrop of what's happening in DRAM, let's say, today. Yes. Oh, yeah, that's a good idea.
What is exactly the reason the industry has chosen DRAM as a main memory?
As a main memory? Well, that's because it fills a space that no other memory technology can fill. Meaning it has very high capacity, very high density, and very low cost. People have figured out how to manufacture it. It has latency characteristics that are much better than many other storage type of technologies like flash memory, certainly hard disks, but not too bad from the processor's perspective also. So it basically has a very nice trade-off between latency and cost and density. That's the reason, basically. It's very hard to replace. We're going to talk about that tomorrow when we talk about emerging technologies also. So it's proved itself very hard to replace.
Okay, so flash memory has bigger latency.
Much longer latencies, yeah. It's you can think of it as on the order of microseconds versus here, where in the DRAM, we're on the order of tens of nanoseconds. Okay, and this are on the order of milliseconds. I'm going to show a picture tomorrow, actually. Hopefully tomorrow. Any other questions? Okay. But that's a good question, basically. The question is basically, is DRAM going to continue? We've talked about a lot of scaling issues. Even with all of those scaling issues today, I guess the path toward emerging technologies, we will talk about that tomorrow. People have been developing a lot of emerging technologies that could potentially replace DRAM, and they've been quite excited about it. Unfortunately, we have not been able to do that yet. I think replacing this technology has proven very difficult. SRAM also has some other characteristics that are very difficult to replace, but that could also be replaced with some other emerging technologies, as we will discuss. Okay. So flash memory is interesting. So if you, based on your comment, I think it's good to also discuss flash memory, because flash memory has been a technology that has been extremely successful relatively recently, right? Early 2000s, I would say, that's where the commercial success began. But flash memory was an idea that was developed in the late 1970s, actually, or early 1980s. So again, why was it able to get into our systems, and why was it successful? Again, it had very nice latency plus cost capacity characteristics. It was much better than hard disks. It was worse than DRAM, but not as bad as hard disks. So it could actually fill a space that's between DRAM and hard disks. So there was a huge gap between DRAM and hard disks. Nanosecond level versus millisecond level. Flash memory was able to get in there with microsecond level latencies. And as a result, I believe it has revolutionized what we have built. Like this, I think, is not possible without flash memory over here. Nobody wants to carry a hard disk inside their pocket, right? Okay. So technology is very interesting. Yes. Yeah, that's a good question, basically. Today, memory controller is here, right? In the memory chip, CPU chips in general. In the past, it didn't used to be that way. In the past, there used to be a separate chip in between. So it used to be CPU, memory controller chip, and then the DRAM chips. But it was still not on the DRAM side. So what if you put it on the reason it got integrated onto the CPU chip was because essentially of Moore's law, right? You have so many transistors. CPU chip started getting in a lot of stuff inside because of the success of very large scale integration and Moore's law. You were able to put stuff, including accelerators, but memory controller as well. That was one of the first things that got into the memory chip. In fact, AMD was the first company that put the memory controller on chip. Intel was quite resistant for years. And then they followed suit because they figured out that AMD's latencies got reduced to memory significantly. So basically, it's in the processor's domain right now. Why not put it on the memory side? I think that's a very good question, actually. And with 3D stack technologies, it may make a lot of sense, right? You have a 3D stack DRAM and the memory controller underneath it. So that's a good question. I think this is basically a good thing to discuss the duties, like who should be managing memory, right? In the current state of things, we're very compute-centric. So our thinking is still very compute-centric. So that's why it makes people, the mindset has been memory controller belongs to the domain of processor design because memory is a dumb device. It doesn't even do control. That's basically the mindset and history of how things have developed. That's the main reason, basically. Because memory is very cost-centric and emerging technologies were not there, like 3D stacking. The way things have evolved is you had DRAM that was just memory. And if you put controller inside there, inside that die, that would be, first of all, very slow because the fabrication technology of DRAM is very different from the fabrication technology of logic. When you put logic in here, logic would be slow, very leaky, very high area. So it would go against the cost of DRAM significantly. That's why the memory controller had its separate chip basically, because that would be a logic chip that you could customize for logic and you could customize DRAM for DRAM. And then that chip got integrated into the CPU or accelerator chips. which makes sense because it's also a logic chip, right? So that's the history of things. But today, with emerging technologies, if you have 3D stacked logic and memory, it may make sense to reconsider that historical design decision. But as we discussed multiple times in this course, reconsidering historical design decisions is very difficult in this domain because it's not just technical reasons, it's also a lot of business reasons and politics. You have to convince many, many people building memory controllers and DRAM to actually buy into that. So it's very difficult. But I think research-wise, it's very good to ask that question. Where should memory controller be? Or should its functions be divided between the processor chip and the memory chip? It's good to discuss that. We discussed actually one idea when we talked about RowHammer, the self-managing DRAM idea, right? That's kind of dividing some of the responsibilities between the memory controller between the processor chip and the memory chip, saying that management functions that DRAM designers are intimately familiar with should go into the memory chip and should be inside the controller over there. And the memory chip should have breathing room provided by the interface so that it can actually perform those management functions. So that's one example of reconsidering the design trade-offs. But unfortunately, it's very hard to convince the entire industry to do that. In fact, it's very hard to convince even the reviewers to do that. You write this paper, and it's actually a beautiful paper that talks about this. But even reviewers are actually their mindset is so much so that, oh, the DRAM chip should not do anything. Because of that history is very strong. Even the research community is actually not very open to that sort of disruptive ideas easily. So we'll talk about the review process later on. So you can see what kind of challenges you face, right, once you have a very disruptive idea. Okay, so here you can see the DRAM controller is on this processor chip, but it's also large. It's pretty large actually for one DRAM. You can see this is Apple's M1. This is quite large. There's a lot of analog and mixed signal logic over here to communicate at low power and high bandwidth using LPDDR. Another example here in AMD. Another example here for IBM. So basically, you can see that this actually occupies a lot of space as well. And there's a lot of pins over here for memory signaling. IBM has a different interface, actually. It's called Open Memory Interface, which enables them to actually scale the memory significantly, but it makes it very expensive also. These systems are a lot more expensive than what you see over here, basically. But basically, if you really want to actually add more memory channels and memory types, you're also bottlenecked by the size of this, right? You cannot basically easily say, I'm going to add 10 memory controllers over here. Well, good luck. Well, actually, existing chips have a lot of memory channels, but let's say multiply it by 10. You're not going to be able to do that unless you increase your chip significantly, which has a lot of other implications in terms of cost and power, right? Okay, so let's talk about DRAM controller. Like what does the DRAM controller do? Clearly, there's an analog functionality, but at the higher level, digital level, it needs to ensure correct operation. Of course, all of this is true for analog level. It needs to ensure it needs to work correctly, right? And there's a lot of work that goes on to the high-speed interfaces. In fact, I believe DRAM is, I shouldn't say something wrong, but I believe DRAM is perhaps the highest speed analog interface and mixed signal interface that we built today in general purpose computing. In specialized computing, maybe there are stuff. But in general purpose computing, this is really the highest speed interface that you build when you communicate between chips. And so there's a lot of effort that goes on to make sure that analog operation is actually correct over here. And that's actually what memory controller designers do at low levels. But there's also a higher level of memory controller design, which is architectural level, I would say. You need to ensure correct operation at the architectural level as well, which is refresh, timing. I would add RowHammer also today over here, basically. The slide is relatively old, but RowHammer is also part of that today. And then that's the correct operation, right? That's the basics you need to satisfy. But then there's also the scheduling functionality, meaning you need to service DRAM requests that are requested by the CPU or whatever is connected to the memory controller. And today we connect many things. It's not just the CPU, it's many accelerators, GPUs, FPGAs. Essentially, there are DRAM requests that are coming from all these sources, and you need to obey timing constraints of the DRAM chips. We've seen some of the timing constraints. We're going to see a little bit more to make sure that, again, things operate correctly. And to be able to do that, you need to take into account a lot of constraints, the timing constraints, essentially. This could be due to resource conflicts, like if two requests go to the same bank, You cannot send both of them at the same time, clearly, as we have seen. Bus and channel and rank, they all impose timing constraints, as well as resource constraints, and different types of delays, like minimum write-to-read delays. There's a write-to-read delay because writes and reads go on the same bus to DRAM. As a result, you cannot do writes and reads at the same time because you need to change the direction of the bus. Again, this is an abstraction level. And that requires time to change that directionality of the bus. So to be able to do this, you need to actually design a controller that's aware of all of these. And also the controller needs to translate requests to DRAM command sequences, because when it gets a request from the CPU, for example, it says, the CPU says, I want this address, right? And DRAM controller should be able to take that address and decide which bank it goes to, which rank it goes to, which memory module it goes to, and then basically convert it to command sequences like I need to do a pre-charge, I need to do an activate, I need to do a read or multiple reads so that I can get the data that this device is requesting. Also, it needs to buffer and schedule requests for high performance and quality of service. This is also a correctness, actually, but there's also a performance aspect so that in order to service things relatively fast, you need to buffer things. And once you start buffering things, you need to think about how do you order things inside that buffer. Because memory is slow, CPUs are fast. You can think of the CPUs as generating things, let's say every nanosecond. Memory is responding every 100 nanoseconds. Think of it that way. If you think of it that way, CPUs, many CPUs are also generating things to memory. As a result, they can overwhelm the memory system. So to be able to service things, you need to buffer the request, right? And once you buffer the request, then you have a scheduling problem. What goes first? What goes next? So a lot of memory controllers do reordering. They do row buffer management, bank, rank, bus management. If you have multiple ranks, for example, you need a switching penalty between the ranks because they also share the bus. So there's a lot of management goes on for scheduling. So scheduling may be just, for example, best effort, right? You can say, okay, first come, first serve. This turns out to be a very bad scheduling policy because it doesn't take into account row buffer, as we will see in a little bit. Okay, you take into account row buffer, you do first ready, first come, first serve, which is things that hit in the row buffer are scheduled first. So that takes into account row buffer locality. We will see that in a little bit. But then that's not enough because you may want to provide quality of service. Some of these applications that require service from memory, that request things from memory, may have quality of service requirements, right? GPU, for example, has a frame rate requirement. You need to satisfy, I don't know, 30 frames per second, 60 frames per second. How do you actually ensure that the memory controller prioritizes that? So many different applications may have quality of service requirement. Your machine learning accelerator that is sending requests to DRAM may have a quality of service requirement because it may actually be performing a safety critical task, right? So basically, there are a lot of issues. Audio, video, they also have quality of service requirements. So many accelerators actually have quality of service requirements, and some general purpose applications also have quality of service requirements, right? When I interact with my phone, for example, I want things to happen quickly. I don't want things to get delayed in the memory controller or SSD or wherever things are being serviced from. So this actually complicates the scheduler. This is performance and quality of service now. And then there's power consumption and thermals. This is becoming increasingly important, actually. So you need to manage power, especially with 3D stacked memories. This is becoming increasingly important with 3D stacked memories because you have logic and DRAM and then many layers of DRAM. And if you're not, basically because of the structure, heat has nowhere to escape, essentially. As a result, this increases the power consumption. And in modern system on chips, actually, it's not just that. It's not just 3D stacked DRAM. You usually have this system on a chip stacked on top of the DRAM. As a result, you have basically a big heat generator, which is system on a chip, heating your DRAM, right? So basically, the power and thermals become a bigger issue in modern SoCs. This is less of an issue if you have like planar systems, right? Where you have processor and DRAM like this, they're far away, and they don't interact with them as much. As a result, the processor is a heat generator, but it's not close to DRAM. So you can see that emerging technology is actually exacerbating some of these issues. This is becoming much worse in systems that look like this. So there's a lot of interesting stuff that goes on stuff like this, basically. Okay, so how do you manage power consumption and thermals? Do you turn on and off DRAM chips? Do you manage the power modes? There are multiple power modes, as we will discuss. This is an area that needs actually a lot more research going forward, in my opinion. We've discussed the idea of voltage scaling, for example, voltage and frequency scaling. Those are ideas that need to be employed, but there needs to be more in this direction. So you can see that if I actually put these correct operation here is about reliability. maybe. This is correct operation in terms of the interface. What does the interface demand? Conflicts. This is performance and quality of service, and then this is power and thermals. So it needs to manage everything. That's one of the reasons why IEDM controller is difficult to design, plus the analog design that we are ignoring over here. So this is what I will just show you pictures, but not go into a lot of details of what each picture does. But this is what a DRAM controller looks like. This is basically showing what I just said. You have many request streams coming from different devices, and then you have an arbiter, and then you need to manage things at a bank granularity, rank granularity. So this is a design choice, basically, what granularity you choose to manage. You may have a single queue that goes to every system, but usually existing memory controllers are managing things at a bank level. That looks like this. So basically, you get transactions, you do address translation to figure out where things go, and then you break the transactions or requests into commands, and then you schedule commands with some scheduling algorithm. And then there's the electrical signaling part, as you can see over here. This is my picture from 2007, or 2006, actually. More architectural, but this is in a multi-core system. You have different L2 caches at the time, but it could be L3 caches also, that send requests to different banks, and there needs to be some sort of interconnect for that. And then each bank has a scheduler, and then there's a global scheduler that takes that prioritizes between the scheduled commands from each bank, as you can see, and sends a selected address and DRAM command to the DRAM banks. And then writes and reads need to be treated a bit differently. So usually these bank request buffers are divided into writes and reads because they have different requirements, obviously, because in writes you need to send the data, right? And reads you just receive the data. That's one thing, but also, as I said, writes and reads cannot happen in general simultaneously on this bus. You need to switch the direction of the bus so that you can start doing writes and then you can start doing reads. So existing memory controllers, they try to batch the writes, and when there are too many writes that are batched, they basically say, okay, I'm going to switch from read mode to write mode, and then they basically try to drain the writes as much as they can. There's some algorithms that are employed over there. Once they relieve the write buffers a little bit, they switch to read mode. So this has clearly implications as to what's happening over here, right? The CPUs are over there, and if you actually are doing a lot of switching to write mode, writes are not as critical for CPU performance, right? Because writes may be write back from the cache. So L2 cache, there was an eviction and a dirty line got written. This has in many types nothing to do with the CPU request, right? CPU reads are critical, however, as long as it's a demand read, a load requested a read, and that needs to be serviced from the memory controller because it's not in the caches. Now that's very critical. That's basically delaying the progress of the CPU. So if the CPU is waiting for a read request and then the memory controller is in write mode, that means that the CPU is getting delayed. So this is unfortunately a problem in DRAM as well as flash memory, but you can see the problem in DRAM, right? Okay, these are areas actually that are interesting to do research in my opinion, how to do the writes and reads nicely. But this also motivates what I'm going to describe, which is a lot of things. Now I've described you some things, like you can think about how to do these things as a human, but there are literally a lot of things to consider over here. Just looking at the slide, you have a lot of things to consider. But even if you look at just these two things over here, there are a lot of things to consider. I mean, maybe performance over here you should look at, but even if you look at these things, correctness issue, there are a lot of things to consider. But you cannot just provide correctness today. You really need to provide performance also, because if you just need to provide correctness, you can actually design a very poor memory controller, right? Because it can basically, for example, say first come, first serve. That's oldest request first. And it can also say, I'm going to obey all timing requests, but you can basically add even more timing slack than timing parameters. So the problem basically is not interesting because your competitor is going to design a much better memory controller. If you actually say, I'm going to design a poor memory controller. That's never the goal. So basically my point is, you cannot decouple the performance and correctness issues as much. You have to design all of these. And today, especially if you're designing an SoC, you have to also consider this as a first-class citizen. Basically, you cannot just say, this is a first-class citizen, oh, performance, I'm going to ignore. If you do that, you're immediately losing market. If that's your goal, of course, right? Or if you're doing research, you're immediately doing something that's not interesting. Let me put it that way. So basically, you cannot say that today. Okay. In the past, there used to be FCFS controllers, like first come, first serve. This is like old Pentium 4, I think. I mean, even Pentium 4 had FCFS, actually. Pentium Pro had FCFS controllers. This also shows you that how memory and processors evolved, right? There were these complicated techniques to do out-of-order scheduling in the processor chips. But in the memory chips, people said for a long time, memory controller chips, I should say, let's do first come, first serve. That's the mindset, right? Processor is important, memory is not important, which we're trying to change. And I think which people are clearly realizing that's not true. Okay, so first come, first serve is old, as I said. So people have quickly figured out that this is not that good. So first ready, first come, first serve says you should prioritize the row buffer hits. This maximizes the row buffer hit rate and maximizes DRAM throughput. But as I said earlier, scheduling is really done at the command level. You basically break down requests into commands, and you prioritize column commands, which are reads and writes, over row commands, which are activate and precharge. So as opposed to activating another row, you try to choose reads and writes that can be serviced from a given open row in the DRAM bank. And within each group of commands, column versus row, older commands are prioritized over younger ones. So that's the idea of FRCFS. Let's take a look at this. So this is really dictated by the DRAM bank operation. If you look at a DRAM bank, which we have seen multiple times, you have a row buffer, which is essentially the sense amplifiers. Initially, it's empty. If the processor or if a request comes to row 0, column 0, you first need to activate row 0, which brings the data into row buffer. I'm going through this relatively quickly because you've seen this multiple times in this course. And then the memory controller sends a column address saying read from this address. Let's assuming it's a read. And the data gets sent from the DRAM chip to the memory controller. That's the column that you want to read, essentially. Now the row 0 is open in the row buffer, and memory controllers should take advantage of it, right? Now you get another address to row 0. This is really a row buffer hit, right? So if there was another address to row 5 over here, the question is, does it really make sense to so assume that this is a younger access, and assume that there was another access to row 5 to the same bank. First come, first serve would actually serve that access to row 5. But first ready, first come, first serve says, oh, row 0 is already open in this bank, so if I access that row, I will maximize the DRAM throughput. So it basically prioritizes row 0's access over row 5's access. As a result, you don't need to activate another row. Basically, you don't need to precharge this row. You don't need to activate another row. You just send a read to the column that you need. And this is called a row buffer hit. And this is actually pretty strong. The row buffer hits are much faster, 2 to 3 times faster than row buffer conflicts. So if the next access is to row 0, column 85, again, this is a row buffer hit. But if you actually need to access some other row, this takes a lot of time. Basically, it's called a row buffer conflict. The row that you're accessing is not the same as what's in the row buffer. So that's why it's a conflict. This is very similar to a cache conflict, essentially. Row buffer is essentially, for all practical architectural purposes, it's really a cache, if you can think of it that way. It has to be there, but it's really caching a row. You can think of it that way. So you need to precharge the bank, which takes time, as we have discussed. In fact, we've discussed the techniques to reduce the latency of a precharge, like low-cost interlinked subarrays, LISA, is one technique. And then you basically activate the next row, which brings the data into the row buffer, and then you send the column command, which is a read in this particular case, to get the data out. So clearly, this row buffer conflict took a lot of time. That's why scheduling matters, basically. Why? Because when you're scheduling, you're basically dictating the priority of requests or commands. I think I talk about requests, but this could be done at the request level as well as command level. It's just a matter of translation, right? Request needs to get translated to commands. But prioritization can be based on many things: the age of the request, the row buffer hit and miss status, the type of the request, whether it's a prefetch, read, or write, the type of the requester. Is it coming from a load or a store? Because this could actually also make a difference in terms of how much the processor stalls, right? There's a lot of techniques that are employed in the processor to essentially buffer stores, so that, because when you're doing just store to memory, you're just writing to the cache. And there are no dependent instructions, at least immediately, right? When you're doing a load from memory, the understanding is that there should be a dependent instruction that's going to get that data. So if it's a load miss, then you're actually delaying those dependent instructions, where store miss, it's not actually clear when the dependent instruction will come for that store. And you can actually do a lot of bypassing techniques internally in the processor, as well as the cache, to reduce the overhead of store misses. So this is also important, as you can see, right? And this is information that's not normally, that you would not normally put in the memory controller unless you're really designing the memory controller together with your CPU. So this is one reason why actually CPU designers like having memory controllers, because they could potentially communicate a lot of this information, even though usually they don't end up communicating that information. And you know by now why they may not end up communicating that information. Anybody? So you're in a CPU company and you don't communicate this really important piece of information to the memory controller. Why could that be? Anybody? So okay, you're in a CPU company. You are a CPU. Let's say you're designing the core, and you say that, oh, I want to communicate the load misinformation to this request. So this request is going to the memory controller because it's missed in the cache hierarchy. I'm just going to add some metadata saying what type of request it is. It's a read request, and it's generated by a load miss. But you don't do that. You don't end up doing that. What could be the reason? Sounds like a good exam question. It's a bit hard to grade, but you discuss, yes. Exactly, yeah. Basically, that's what I was looking for, essentially. Because you're not working alone. You're not designing the entire chip. You're just designing the core. And then somebody else is designing the memory controller, and you don't agree. Or maybe you don't even talk to each other. First, you have to figure out who to talk to. And then you have to basically agree on that interface. But yeah, absolutely. This is actually a very, very practical, real concern. Even though it looks like it's very easy to do on a single chip, if you don't have, let's say, a good communication mechanism in your company, and many companies actually don't have this, frankly. Startups may have an edge in this if they actually build the culture right. But yeah, this is one of the major reasons why things don't get communicated. Things get compartmentalized, and then people don't want to change stuff. Basically, it's working nicely, right? If I get this information, what do I do? Okay, you agree on the interface, and then the person gets that information and doesn't use it. That's another common thing that happens, actually. They agree, okay, I'm going to receive this, but I'm not going to do anything with it. Because that's easy for them to do, right? Well, this information normally doesn't go there, right? This basically says a request is generated by a load or store. Normally what happens is you don't even have this information at the cache level, right? Normally the CPU injects a request to the memory hierarchy, and it basically says it's a read. Let's assume that it's a read request in this particular case, right? Because store misses also generate a read request from memory because you need to read the cache line from memory. So in the L3 cache, basically, you get a request saying, I want this cache block. You have no idea whether it's due to any of these, basically. So to be able to do that, you actually need to communicate this information through the cache hierarchy and all the way to the memory controller. So you don't actually go through, you probably go through 3 groups in a big company because CPU plus L1 and private cache that's belonging to the CPU is one group. And then there's the L3 and interconnects on core parts, and memory controller can be a separate group actually by itself. Yeah. So these are some realities in real life that you may find out. You may have a great idea, but that great idea may never get implemented or may get implemented 10 years down the road. This should not discourage you, but you should be prepared, basically. Okay, request criticality. This is actually very important, whether a request is critical for performance. So load misses are kind of critical, but there could be other criticality metrics that you develop, right? For example, if I actually delay this request, a dependency chain that's very long will get delayed, as opposed to if I delay other requests, only one instruction will get delayed. And maybe that instruction is not on the critical path. Why? Because you may have a load and you may have a branch that's dependent on it, and you've already correctly predicted that branch. Essentially, that you don't know whether you're correctly predicted, maybe. But if your branch prediction accuracy is high, you may say that, okay, I probably correctly predicted that branch and it's not on the critical path. So maybe this request is not as critical, right? So you can actually guess some information about which requests are critical to the progress of the instruction stream that's executing in the CPU. And you may again want to communicate this, right? So these are actually very interesting things. All dismiss is also maybe more important. Will it stall the processor? This is actually a very complicated problem. How do you predict the criticality of memory requests? Ideally, you would look into the future and figure out which one is more critical and prioritize the requests that are most critical for performance, let's say, if that's your optimization goal. But this is an interesting problem that requires more work also. We'll discuss more on this, but what kind of interference are you causing to other cores? It's actually interesting because it may this core may not be the only core that's generating requests clearly. There are multiple cores, and the interference you cause to other cores may delay some other core. Now it's actually becoming even more complex. And then who knows what else. So we're going to talk about some of these in later lectures, especially if this becomes a big problem. And this actually becomes an even bigger problem when different systems components go through the memory controller. Today, for example, network controllers also go through the memory controller, because when you get a packet from the network, you need to direct memory access that into the memory so that it gets processed in the CPU. So now you have interference from the network between the CPUs and the network requests. Now, which one is more critical? Well, depends, right? If your network is extremely high bandwidth, maybe you're delaying that a very high bandwidth network that is supposed to be operating at a high bandwidth. So there's a lot of interesting things. Actually, storage controllers also go through the memory controller, because whenever you do a request to an SSD, you need to bring the data into memory, and that goes through the memory controller again. These are direct memory access paths that go through the memory controller, and then there's the CPUs and accelerators that are also accessed. So that's one of the reasons why memory control is actually quite complex today, and quite important also. You can think of that as it's kind of the center of the universe, right? You have this memory controller, and everybody has to go through the memory controller to communicate with memory. And today we do a lot of communication through memory. You could argue that maybe that's not the right thing to do, right? Why does the network controller go through the memory? Why not have some other processor in the network? And people are trying to do that. And I agree that that makes sense. Basically, decentralized processing would be better. But today we have a lot of centralized processing because we've been very compute-centric, right? Okay, so let's take a look at row buffer. Even if you look at the row buffer management policy, there are actually a lot of things that you can develop over here. Let me give you very simple ones. Open row policy says, after you access a row, you activate it, and you've done a read, you service the request, keep the row open after that access. In the anticipation that, so this anticipates that next access may need the same row, and this becomes a row hit, so that's good. But if the next access needs a different row, now what happened is by keeping the row open, you caused a row conflict and wasted energy. You could have actually closed the row right away after you did the first access. The question is, do you know what's going to happen in the future? You may not know, right? If the next access to the same bank is already in the request buffer, you can actually look at it and basically keep the row open. So basically, you can actually make this a bit smarter. Closed row, in a reasonable implementation, you close the row after an access, assuming there are no other requests are already in the request buffer that need the same row. So basically, you do a little bit smart closed row. Because if there's already a request that is needing the same row in the same request buffer, you may want to just service that, right? And then close the row when there are no requests in the request buffer to the same row. So again, here the anticipation is that next access might need a different row. You avoid a row conflict by closing the row immediately. But this works badly if the next access might need the same row. This leads to an extra activate latency. So open row is actually good for, open row policy is good when you have good row buffer locality in your request stream, and your memory controller can actually exploit that locality. Closed row is good if you don't have good row buffer locality in your request stream, and the memory controller tries to exploit it, but it doesn't find it, essentially. But these are two extremes, right? You can also have adaptive policies that predict what's going to happen, right? Predict whether or not the next access to the bank will be to the same row and act accordingly. And people actually developed this. A lot of existing memory controllers have this sort of prediction mechanisms. Again, you can read patents and there are papers on it also. The question is, how do you do the prediction now, right? So it's interesting, basically. Even if you look at just a row buffer management policy, which is a very small fraction of what you're doing, small but the important fraction, there are a lot of policies that you can develop. And then the question becomes, what is more important, right? As a human, how do you develop this policy, right? You're going to come up with a lot of heuristics, perhaps. Okay, maybe you optimize this. But there are 20 other things that you're going to optimize in the memory controller design, more than 20 actually. Okay, so this is just an example of what happens. I will not go into detail, but this basically is kind of a simulation of if you have this policy and if your first access is to this and next access to this, what are the commands that are needed for the next access? So for example, if you have a closed row policy, if your first access is to the row 0 and the next access is row 0 and the access is not in the request buffer, you close the row and the command needed for the next access is activate the row again, read and pre-charge. So basically you've done the wrong thing over here by closing the row too early. But if you have a good policy that has anticipated that the program, for example, has very good locality in the row, it would not use closed row policy in this particular case, right? So you need to take into account workload characteristics when you're designing these policies, and that makes things more complex. And also the system characteristics, because workload may be one thing, this is maybe one workload, but then what if you have multiple workloads that are accessing the system, accessing the memory controller at the same time? That complicates things. Okay, so this gives you a glimpse of the performance, right? And then there's power. DRAM chips have power modes. Basically, the key idea is when not accessing a chip, power it down. Now, increasing there's voltage and frequency scaling you can potentially employ. I'm not going to talk about that here. I think there needs to be more work done in this area also, power modes, power states. This is very coarse grain in existing standards. So there needs to be more work here. But basically, when you're the highest power is consumed when you're accessing DRAM actually. That's not here. But to be able to access DRAM, you need to keep the bank in an active state. And that's the second highest power. And then you can make the banks idle. That's that's the third highest power. And then you can power down things. Now that's less power. And then you can basically shut down everything except for refresh circuitry that refreshes DRAM. That's the lowest power state in existing chips. But now you also see the trade-off, right? Whenever you want to transition from one state to another, you incur high latency during which the chip cannot be accessed. For example, if you're in self-refresh mode, it may take microseconds to get out of this mode, activate the bank that you want, and then access the bank. When you're in power down mode, it may take, I don't know, some hundreds of nanoseconds to get out of that mode. When you're in active mode, there's no latency penalty if you want to access a bank, basically. So there's a trade-off between power savings and latency to access DRAM, essentially. And that trade-off needs to be navigated nicely. And that's part of the difficulty also, right? Once you include power in the equation, it becomes even harder. And I don't believe that these are the best power states, actually. There needs to be more research, as I said, in this direction. Any questions? Yes. Oh, okay. This is a question for Giray, but he's busy writing his paper. All banks idle and self-refresh, you said? Well, okay, that's maybe I'll take it. I'll not put Giray on the spot. But basically, these two are very, very similar with small differences. You can read the standard. It's not, but self-refresh says, I'm going to turn off everything except for the refresh circuitry. So all banks idle is actually you turn off all of the row buffers, but not the other circuitry that enables you to activate the DRAM. So activation circuitry is still on. So there's a lot of leakage that happens in those circuitry also. Does that make sense? Here you turn off even the activation circuitry, so you need to actually power that up so that you can access it in self-refresh mode. So for example, my phone right now is probably in self-refresh over here, hopefully, if the memory controller is doing its job. Yes?
Basically, how you decide which one?
Yeah, that's basically the job of the memory controller. Again, memory controller can say, for example, I haven't accessed DRAM in a while, so I'm going to turn off DRAM, right? That's what this should be doing. This guy hasn't accessed DRAM in a while, so let me turn off everything except I should refresh, basically. Right? So that's basically an example, right? You predict basically. Usually these are based on prediction. Yeah, and there are papers that are written on this prediction, etc., which I will not go into. It's similar to voltage and frequency scaling also, right? When do you go to lower voltage and lower frequency? When you're not using the DRAM bus, for example, that's a simple prediction mechanism. Or you employ a performance model like we discussed in the Voltron paper last week. But usually in existing controllers, those performance models don't exist. Usually they're simple heuristics. They say, oh, I haven't accessed DRAM in a while. Let me go into the next power state. Okay, so now you can see that you need to design these things. Any other questions? Okay. Each slide I cover over here has tens of papers written on it. Let me put it that way. And there are a lot of patents also. Okay, so basically why DRAM control is difficult to design. If I haven't convinced you yet, you need to obey the DRAM timing constraints, and there are many timing constraints. I'm going to show you some more. Write to read, TRC we already discussed, write to read we already discussed. Basically, TRC is rogue cycling. This is the minimum cycle of number of cycles between the issuing of 2 consecutive activate commands, right? We try to reduce it a lot in low latency memory. But there are 50 plus, actually 100 plus timing constraints in modern DRAM. On top of this, you need to keep track of many resources to prevent conflicts in the resources, channels, banks, ranks, data bus, address bus, row buffers. So if you do subarray level parallelism, subarrays also go here. So they actually, some of the ideas that we've discussed actually complicate things. You need to handle DRAM refresh and RowHammer. We should all add RowHammer over here at this point. That's the interesting thing about RowHammer, right? There are slides that don't have RowHammer. They should really be updated with you need to handle DRAM refresh and RowHammer, basically. Because that's now in the standard, basically. In the standard there, in the memory control needs to handle RowHammer. You need to manage power consumption, as we discussed. And on top of this, you need to optimize performance and quality of service. And this adds more complexity because reordering actually is not simple. And adding fairness and quality of service and guarantees complicates the scheduling problem significantly. So these are some example timing constraints. You already know why timing constraints exist, but I just use a reminder, and I'll give you some papers you can read. Some of these will be, some of these we already discussed, actually, these two, subarray level parallelism and tier lates DRAM. These actually discuss the reasons for timing constraints nicely. So this is from the tiered latency DRAM paper. You can see some timing constraints. For example, activate to read, activate to write timing constraint is TRCD. It's in some DRAM standard, DDR3 1066, it's 15 nanoseconds, for example. Activate to precharge is a bit longer, as you can see. And you can see that this is where the timing constraint, you can basically visualize these timing constraints also. This is TRCD. Activate to read. Why does this happen? Because once you activate a row, you need to be able to get the sense amplifiers reliably sense, to have the sense amplifiers reliably sense the data before you can issue a read. So all of these timing constraints are there to enable reliable operation. You have to wait some amount of time to ensure that you can issue a read. Otherwise, you will not get the right data, or you're not guaranteed to get the right data. And we've already discussed that there's a lot of margin that's added to these timing constraints, and we've kind of tried to reduce it, right? Okay, so there are many timing constraints. But you can also question this, right? As a researcher, you say, why do I want all these timing constraints, right? Why not have a single timing that says basically, regardless of whatever I'm trying to do to memory, I just have a single timing constraint that basically says, I'm reading, I'm writing, it doesn't matter what I'm doing. I'm going to abstract everything with a single timing constraint saying, this is the memory access latency. What's the problem with that? Or if it's good, what's the benefit of that? Yes. Exactly. Basically, what you're getting at is that timing constraint needs to be the longest possible thing that should correspond to the longest possible time that the DRAM needs to respond. So that's the problem, the single timing constraint. That's why this has evolved this way. All of these different operations have different timing constraints. But you can also say that, okay, maybe I don't have a single timing constraint. I just have an asynchronous interface. So timing constraint, by definition, implies a synchronous interface. You basically know how long something is going to take. And based on that, you design the memory controller to take the next action, right? But you can say, forget about these timing constraints. I just want to be asynchronous, meaning memory controller sends a request, and the DRAM basically returns the request using some acknowledgement. It could be any time. There's no single timing constraint. It could be 5 cycles if the request takes 5 cycles. It could be 215 cycles if the request takes 215 cycles. Now that's becoming more interesting now, right? Now that's a much more flexible interface compared to this very, let's say, nitty-gritty synchronous interface. And then the question is basically, what do you do? So what are the benefits of that interface, that asynchrony? Yes? On the DRAM side, probably. Now the memory controller maybe goes on the DRAM side, right? The DRAM may actually be doing some things internally, right? So it's good to think about it. This asynchronous interface actually is a much more flexible interface, but that's not how things have evolved as much. In the past, it used to be that way, but then memory controllers, people wanted to design memory controllers, again, because of the dichotomy between logic and memory and very different fabrication technologies. People really wanted to have a synchronous interface to really optimize the command scheduling. So where do you put the command scheduler? Again, it needs to be on logic chip. So to be able to optimize optimize the scheduling of commands in that logic chip, you really need to have this synchronous interface. Otherwise, once you go to asynchronous interface, then basically the DRAM chip needs to be doing the scheduling. And again, putting a scheduler inside the DRAM chip is not good for fabrication, essentially. Okay. So we covered a lot of interesting things, actually. But maybe there's a sweet spot somewhere, right? This is very, very synchronous. Maybe there needs to be some asynchrony. And again, self-managing DRAM is an example of trading that synchronous or trading off some of the synchrony for asynchrony. It gives DRAM an ability to reject commands saying that, oh, I need more time to do this stuff. So don't bother me for a while. Okay. So I think we've discussed why there are timing constraints. Remember this picture that I showed you last time when you get an activate, there's stuff that happens. The bit line shares the charge, and then the sense amplifier gets enabled that amplifies the charge. And after some point, you can read the data reliably. And actually, you can read the data perhaps early, but usually manufacturers put a guard band because of the variation as we discussed, right? So the timing constraint gets determined by that guard band as we have discussed last time. So you can do this for many, many different timing constraints, which we will not go into, but TRCD is one example. Again, this is a sub-array level parallelism paper. This also shows nicely the timing constraints, at least the major timing constraints in a DRAM chip. You won't find this nice picture in a DRAM data sheet. How many people have read DRAM data sheets here? Okay, Geraldo raises his hand because he knows how painful it is, right? If you want to understand stuff, that's not what you go and read. Well, but you have to read it, of course, but it's not, let me put it this way, it's not written for clarity of understanding. Yeah, that's true for a lot of documentation, actually. How many people have read ISA manuals, like x86 manual? Okay, good. That's also usually not written for clarity for understanding, but it's much better than DRAM data sheets, I should say that. It's actually much cleaner in many cases. Okay, but basically, it's good to have these works that describe things in a more clean way, let's say, and you can read the paper. So this basically describes what are the timing constraints for read to write, write to read. And there's a scope of the timing constraint also. Not all timing constraints are at the bank level. For example, the TRCD that we discussed at the bank level. But there are channel level constraints, there are rank level constraints, because these actually relate to the bus. So read and write, for example, as we discussed, write to read delay and read to write delay. Why do these look so bad? Do they look bad from that side? I see grains of things here, whereas this is much cleaner here. Like this. I mean, Geraldo, you would appreciate this. How does this look? Can you read it? I think there's something wrong with the projection quality. We should fix that during. Yeah, it's very grainy here. I mean, it looks perfect over here. It's not because of a copy paste error. It's a projection quality problem. Yeah, but that's TCCD and T read to write, for example. So these are ranked level constraints, and these are fairly long, as you can see, right? It's 15 nanoseconds, which is very similar to an activate latency. Okay, but you can find more. So basically, DRAM controller design is already difficult. It's already becoming. It's also becoming even more difficult if you look at the system level picture, right? So basically, you have lots of different requesters as well today. And it's not just a single CPU; it's many CPUs and many different CPUs, perhaps running different applications, and clearly GPUs, hardware accelerators, and you can keep adding stuff. And what this doesn't include is the DMA engines, for example, which we should really update to include also. So yeah, basically many agents and many timing constraints and many goals at the same time. Okay, so maybe I'll cover this and we'll take a break at the end of this lecture. So we're going to cover actually the quality of service issues. And I think it's good to think about that, let's say prefetch that. But I'm going to focus on just performance right now. Even performance is not easy, basically. So basically, it's difficult to design a policy that maximizes, let's say scheduling policy, that maximizes performance, quality of service, and energy efficiency. there are basically too many things to think about. As a human, you have limited resources, and you basically have continuously changing workload and system behavior as well. Basically, workloads change and system behavior changes. System constraints change also, right? A lot of things are dynamic in today's systems, right? You have dynamic voltage and frequency scaling, and the pressure on the memory changes once you have dynamic voltage and frequency scaling in your CPUs and accelerators. So there are a lot of things to change, essentially. So wouldn't it be nice if actually you had a DRAM controller that automatically found a good scheduling policy on its own? You could change that scheduling policy to power management if you want. I don't know, maybe RowHammer management. It's good to think about these things, basically. How can you actually automatically do these things as opposed to a human designer going and trying to take into account this multi-dimensional, or actually many-dimensional space with many, many constraints? It's actually a big mess. So maybe I'll, yes, please. Yeah, okay, reinforcement learning. Yeah, that's what I'm going to talk about, as I said earlier. But maybe I'll give you an anecdote over here. So a lot of people have tried designing DRAM controllers. So some really good system designers. How many people know the name Charles or Chuck Tacker here? You guys are all young. How many people know about the Xerox Alto system, for example? Nobody? We're talking about 1970s here. Yeah, when you were born? Okay. Some people have not been born at that time, probably. But basically, these are precursors to modern PCs. PCs like desktop PCs, right? So this is in the Xerox labs in Palo Alto, people were developing these PCs that essentially they were imagining things. They were developing what's called the Alto system, and Chuck Tacker was one of the chief architects of that system. He actually won the Turing Award in 2009. I believe 2009, I'm not sure. Don't quote me on that, but I believe it was around that time because of his early work on these systems. So he actually designed a lot of things in his life, but while I was at Microsoft Research, he was also at Microsoft Research. And we had a lot of discussions because what he was doing while he was at Microsoft Research toward the end of his career was actually designing an FPGA board so that you could simulate systems. So this ties into the next lecture. So you could simulate full systems by accelerating simulation on the FPGAs. So he was designing the FPGA board for this simulation engine, but what he was focusing on for a good while was DDR3 memory controllers on that FPGA board. So he was designing this DDR3 memory controller, and he was basically saying that this was the hardest thing I've ever designed in my life. This coming from a person who actually led the design of some of the first PCs. And I think I would agree with that. These are some of the, if you want to optimize things, memory controllers are actually perhaps some of the hardest things that you design today. Yeah, I'll leave it at that. If you want to optimize things, I should say. If you don't want to optimize things, nothing is hard to design. Everything is easy. Yes, please.
Why are the memory controllers not implemented in the operating system, like maybe together with the page tables?
Well, operating system like in software or? Yeah. Yeah, I don't quite understand, like what benefit would you get by doing it with the page tables? Because these provide different functionalities, right? Oh, okay, I see. Yeah. I mean, possibly, you could expose things from the memory controller to the operating system, I think, and potentially co-design the system-level memory management policies with the memory controller policies. And there's actually research in that direction, for example, to partition the pages across different memory controllers to solve some of these issues. I think you're getting at things like that. It's possible to do that, yes, and there's research proposals, but that's even harder, basically. That's adding one more dimension to the problem. That's already multi-dimensional, right? So I have not even talked about that, but yes, that's a good question. That basically complicates the problem without solving any of these. Yes. Mm-hmm. I don't know what it would be. Think about it. I mean, memory control used to have its own chip, as I said, right? You could do a lot of things over there, but in a sense, this is a latency critical component also, right? Because DRAM, you don't want to increase the latency. Once, for example, when AMD put the memory control on chip in early 2000s, they basically report a 30% reduction in memory latency. And that's a big reduction because you don't have to go through another chip. Once you start delegating some things to other chips, it has to be not latency critical. Yeah. That's why SSDs can tolerate some of these things, but people are even trying to get rid of additional communication to the SSD controller so that they can reduce the latency to the SSD as well. That's a good thinking, but I think it goes against latency in general. Okay, so let's talk about the stream a little bit, and then we're going to take a break. But basically, we're just looking at the performance function, not even other stuff, energy, power management, etc. Memory controller's job is to resolve memory contention by scheduling requests. The question that we're going to look at is how to schedule requests to maximize system performance. This is the idea we had in 2007 or so. Basically, the problem we've discussed. Essentially, it's difficult for human designers to design a policy that can adapt itself very well to different workloads and different system conditions. And the idea is to have a memory controller that adapts its scheduling policy to the workload behavior and system conditions using machine learning. And the key observation is what kind of machine learning, of course, right? And the machine learning here that we use is reinforcement learning that maps nicely to memory control. And this is a paper that we're going to assign. You can read it in more detail. Reinforcement learning maps nicely because of what I will show you in a little bit. But basically, we're going to design the memory controller as a reinforcement learning agent that dynamically and continuously learns and employs the best policy to maximize long-term performance. That's the idea. So what's reinforcement learning? Well, all of us are reinforcement learning agents, actually. You can put yourself over here. You're interacting with the environment. You're observing some state, taking an action, and getting rewarded. Maybe delayed in a delayed manner, but maybe some immediately also. And based on that, you're adjusting the actions you're going to take in a given state. Right? How many people know about Pavlov's dogs? Okay, so Pavlov basically trained these dogs. These dogs basically, Pavlov figured out that dogs would react to a bell as they would react to food. If you actually provide the bell, rang the bell, and then provided the food right afterwards. So he conditioned the dogs such that they would learn that whenever there's the bell that rings, they're going to get food. Right? So that's an association, for example. You could actually train that. This is how we work also, right? I put my hand on a stove. I figure out that I should not do that, assuming that I know the state of the stove, right? That's against state. Given the state of the stove is hot, I do not take the hand putting action on the stove, right? And then I get a reward or I avoid punishment, basically. That's the idea. So I can train humans or animals like this. And actually, some people in psychology believe that humans are just reinforcement learning agents. Basically, nothing we do is beyond, that's the only form of learning. B.F. Skinner, for example, he's a very famous psychologist in learning theory. He is a very, let's say, he was a very hard-headed person saying that nothing we do is beyond reinforcement learning. If it looks like something beyond reinforcement learning, that's because we don't understand it yet. Now, that's a very tough thing, right? How do you prove this theory? That becomes a little bit difficult. But basically, B.F. Skinner actually was, he did a lot of really interesting things. And one of the things he did was he was able to train pigeons to deliver messages, critical messages during World War II. So you can actually read about this. This is very interesting stuff. Using reinforcement learning principles again. So basically, that's reinforcement learning. You have an agent interacting with the environment and basically optimizing its policy over time so that it's maximizing its rewards or avoiding punishment. You can think of punishment as a negative reward also, right? Essentially, memory scheduler looks like that also. So there's reinforcement learning theory that is based on the reinforcement learning theory in psychology. But basically, you have a scheduler that interacts with the system that takes an action, which could be the scheduled command, or that takes no action, which could be nothing, no op, as we will see, and observes some rewards which is going to be the data bus utilization in our case, based on a state. And then basically it optimizes policy so that it maximizes the data bus utilization reward in the longer term. So this way, actually, you can optimize for long-term rewards also. You're not optimizing for the immediate reward, but long-term rewards. And for that, you really need to understand how this works. But basically, you weight the rewards that accumulate over time, and you optimize that function that has a weighted reward in the end. So that's the idea, basically. Once you have this idea, you apply some reinforcement learning mechanism. I'm not going to go into the details of it, but of course, you need to optimize the system because this is going to be implemented in hardware, right? So essentially, you associate system states and actions, commands with long-term reward values. Each action at a given state leads to a learned reward. You can implement this using a table. If I take this action in this state, what kind of reward am I expecting to get based on what I know so far? That's the idea, based on my experience so far. So this could be implemented as a table, basically, table lookup. And then you keep updating the values based on the state and action pairs you observe. And then you schedule the command with the highest estimated long-term reward value based on that table lookup. And then you continuously update the reward values for the state action pairs based on feedback from the system. So, of course, here there's a lot of interesting trade-offs, right? How do you actually explore versus exploit? Do you always follow this policy? This is a very common thing in machine learning, exploration versus exploitation, right? Do you always follow this policy, or do you sometimes pick some random action to explore whether you're actually doing the right thing or not? So that actually enables learning. Exploration helps learning, and this memory controller has some exploration. Also, generalization is important because human beings generalize, right? And also reinforcement learning agents should generalize. How do you incorporate generalization in a hardware table? And you can read the paper about that. That's also interesting. Basically, you cannot represent state at a very fine grain. Basically, you normally represent the state with a quantized value. We'll see the state in a little bit. But you need to represent the state in a coarser grain value, which should not reduce your accuracy. But you also need to play some tricks with the tables, as we have discussed in the paper, which I'm not going to go into. But this is a paper. But let's take a look at what's important at the high level. So reward function is very important. Whenever you design a reinforcement learning agent, you should set a good reward function. In this case, reward function is easy because we've kind of simplified the problem. Basically, our goal was to maximize data bus utilization. We will see in a couple of lectures that this is not a great goal when you have multiple applications running in the system. They have different requirements. Your goal should not be to optimize data bus utilization. But when you have a single application running, this is actually not a bad goal. So basically, you get a reward, a positive reward when scheduling read and write commands, meaning you're actually utilizing data bus. Otherwise, you get 0. And the goal is to maximize that in the long term. And then the state attributes. How do you decide what are the state attributes you're going to observe? This usually happens with feature selection, and we have a static feature selection method. But this could potentially happen online also, or automated manner. But you can see some of the state attributes that we found are important based on feature selection, number of reads and writes and load misses in the memory request buffer, number of pending writes, and essentially this is called reorder buffer heads. Basically, all the instructions that are waiting for the reference to row currently. This kind of, you can see that these are taking into account some criticality and the request's relative order in the instruction stream of the processor. This may be taking into account criticality also. So here you need to be careful because, I mean, this is really important clearly, but this is also important because if you really want to get to a good policy, you need to explore a big state space. For example, if you did not include some of these things, maybe the feature selection process would not actually choose them. Well, it would not choose them, perhaps. It could combine other features to get that information potentially, but it's easier if you actually include lots of state features that the feature selection process can select from. So this is where actually domain expertise is really important, clearly. And then actions are easier, I would say. These are the actions that memory controller takes. Refresh is handled separately, so you can read the paper. So I will not go into more detail, but you can see that the performance results are actually quite good. This is in order. As I said, in order is bad. This is first come, first serve. And first ready, first come, first serve is significantly higher. And this is self-optimizing memory control. Basically, you get significant performance improvement. And then that's also true for other policies. And also the performance improvements are robust. But I will let you read the paper. I don't want to go into a whole lot of detail on the design. Any thoughts? before we do some analysis of this? Yes. Read or write, yes. That's correct, yes. Yeah, so reward just basically says if I have scheduled a read or write, I get a positive reward. And then you accumulate this over the long term. Exactly, yeah. You still obey the timing constraints. I mean, timing constraints are there when you schedule things. Yeah, I mean, you could define the reward completely in terms of latency also. Later work actually does that. But yeah, that's a different way of defining the reward, yes. It may not be that easy. You need to come up with a function probably, right? Yeah, I think once you start complicating the rewards to take into account latency, it becomes a little bit difficult. But yes, I agree. I think this is not necessarily, basically our goal was to really maximize data bus utilization, not minimize the latency, for example. That's another goal. Quality of service could be another goal, right? Actually, later work builds on this to provide quality of service. There's a Morse work. So yeah, reward function needs to change based on your goal. Yeah. Yeah, maybe you'll come up with a new mechanism. Think about it. Yeah. Yeah, you need to read the latest papers in the area. Okay. Okay. So let's take a look at the upsides and downsides, and then we're gonna take a break. But basically, the big upside here is you have continuous learning in presence of changing workloads, environments. So you're not stuck with a simple heuristic-based policy, basically. My memory controller, for example, in my pocket is employing the same policy for I don't know how many years. This memory controller over here is employing the same policy for how many years? Regardless of whatever it's seen, doesn't matter. It hasn't learned anything. Basically, it's extremely stupid, if you will, right? A designer said you should do this, and it's doing this, and that's it. It hasn't learned from the environment, workload, my behavior, nothing, basically. It feels like a huge missed opportunity, right? So also designer burden reduces because now the designer just needs to figure out what I just discussed over here, right? Reward state actions, which may be difficult, no question about that. But I don't believe it's as difficult as coming up with a policy that could consider a lot of these system variables and targets, etc. So basically, designer specifies what system variables might be useful and what target to optimize, but not how to optimize it. That how is very difficult, I think. So of course, the difficulty is now, what about the objectives, right? What is your goal? How do you actually satisfy and specify different objectives? Fairness, quality of service, etc. What is the hardware complexity? There's hardware complexity analysis in the paper. It's not that bad, actually, if you design it carefully. But still, it's more complexity compared to existing controllers. And perhaps more importantly, I'll go back to mindset, but this is not the way people design things, basically. This basically disrupts a lot of things in design and design flow also, testing. For example, how do you test this sort of controller? It becomes difficult. Right now, you have test suites, you input, and you know exactly what's going to happen. Whereas if you have some other test suite, you provide some inputs. Well, at the table level, you know exactly what's going to happen. But at a higher level, you don't know exactly what's going to happen, right? You have to simulate the reinforcement learning agents. So essentially, the testing becomes much more difficult to do. Verification becomes difficult. So this actually disrupts the design mindset and flow. That's true for a lot of learning-based controllers. Because it doesn't become a simple input and output relationship. It becomes something else. Because at least over time, longer periods of time. Right? Anything else? Yes. Yes. Yeah, this is in hardware because memory control needs to react quickly, right? You cannot do this in software, yes. I mean, you can do this in software, but it will be very long latency to manage. Yeah. How are you wiring it? So you need to read the paper. Yeah, the paper describes basically you need to be careful in how to access things and pipeline and parallelize things. Yeah, that's a good reason to read the paper. How many people are interested in this stuff? Is this interesting, boring, somewhat? Don't be shy. Okay. I'm not going to ask who's not interested because I know who's not interested. Okay, that's good. When I don't ask, she's interested. When I ask, she's not interested. This is like quantum state observation, right? When you observe the state, you change the state. Okay. Okay, so you can read the paper. I think this is an example of a self-optimizing data-driven computing architecture, which we will talk more about. I will give the high level. Basically, a lot of the system architecture design today is very human-driven. Humans design the policies. As a result, we have many too simple short-sighted policies all over the system, actually. If you look at hardware, this is definitely true, with very few exceptions, like perceptron-based branch predictors that exist in some systems. If you look at software, this is mostly true also, actually. A lot of the software, like if you look at the operating system, lots of policies are basically, actually, I believe almost all of the policies, maybe some prefetching policies in some places, don't use heuristics that are designed by humans. As a result, there's no automatic learning. There's no experience-driven learning. And essentially, you cannot take lessons from past actions because the systems are not designed this way. So the bigger question is, can we design fundamentally intelligent architectures that can learn from their actions and that can do better things over time? This is actually good because this also enables systems that get better over time, right? It's like online profiling. Online, you figure out things and the system becomes better over time. There's also online learning. The system becomes better over time because of the policies that are employed. So I think an intelligent architecture should be more data-driven, like this is an example. Machine learns the best policies and how to do things. And hopefully this leads to sophisticated workload-driven, changing far-side policies and that employ automatic data-driven policy learning. And ideally, all controllers are intelligent data-driven agents. Whatever you design is making a decision based on data as opposed to human, what's dictated by humans. And then they need to coordinate, of course, with each other also, because you don't want a learning agent that's making a decision, another agent that's making another decision. And because of the lack of coordination, they're making contradictory decisions for the overall system, right? That's also very important, actually. Okay, so if you're interested, there's more. I think we're going to actually cover these in later lectures. This is an example. Where's Rahul? Okay, he's not here. He gets a minus point. I'm just kidding. He did a lot of this work for prefetching. And then we have Rakesh was involved in, Gagan is not here, on self-optimizing hybrid SSD control. So there are actually a lot of interesting things that you can do. And this was also Rahul's work that was presented a couple of weeks ago at Micro, which got the best paper award also, which he's going to present hopefully in a research lecture over here. Okay, so I think I'm going to skip this because we are running out of time. But I think it's good to think about like this system also. This system also makes a lot of decisions. As I mentioned in an earlier lecture, people who tried to understand humans and this system were very inspired by computers in, let's say, 1980s, 90s, maybe starting from 1970s, actually. But they're not anymore because they figured out how bad computers are in terms of how they resemble this. Basically, you cannot look at a computer and try to understand what this is today. That connection. Computing as a paradigm to understand humans is gone, basically. Whereas people were quite excited for some point, at some point. And I agree with that because it's actually a much more, let's say, intelligent system than what the computing systems that we build today are. Okay, but I think if you really want to do this, you need to rethink the stack. So this is a paper that we may assign at some point, but it's a very short position paper that talks about this data-driven, data-centric, and data-aware computing. Okay, let's take a break right now, unless there is a burning question. Okay, let's take it, I guess, 15-minute break. Let's start at 58. Yeah, I'm not sure. That's a good question, basically. Yeah. I think that also shows that it's a good research topic. Yeah. Yeah. I don't think that's a huge obstacle, but it's an obstacle that needs to be solved, let's say. Okay. Okay. Okay, let's get started. So now we're going to talk about simulation. I was hoping we would have more time for it, but that's okay. Any questions on the prior part of the lecture? Or lecture 11A on memory controllers? Processing in memory, yeah. Mm-hmm. Yeah. Mm-hmm. Yeah, I mean, processing in memory changes certainly things, right? Because now you have processing and you can add controllers over there. So there's a lot of other stuff. I think that processing in memory takes a very different approach to memory control. It basically just says we're going to do processing. And once you can do processing in the memory controller or in memory, you can also do a lot of these functions, basically. So I think it simplifies. It's a different mindset, let's say. It breaks free from this processor-centric mindset that has been dominating the memory controller design also. So I think a lot of things will change in memory controller design with processing in memory. Yeah, system also. Yeah, you may need some meta controller also that manages things, different distributed agents. Yes. Yeah. Yeah, there's a lot of ideas to explore, basically. Okay, now let's move to simulation. So I wanted to spend some time on simulation. I think this is important. Last year, we didn't have much time to discuss this. So I brought it back with some more, let's say, information. And you've been doing a lot of simulation in your labs. How many people are doing the labs? How many people are not doing the labs? If you're TA, don't raise your hand. Okay. Yeah. Okay. I think in labs, you learn a lot. And the first few labs are, well, I guess the cache labs are relatively easy, let's say. How many people find it easy? Maybe, okay. No, not so easy. Yeah, if you've not done simulation, then it may not be easy, but you get used to simulation a lot. In the past, we used to have Verilog labs also, and then Verilog and C labs, and then we got rid of Verilog labs. I don't know, maybe we'll bring them back at some point. But now we have a new lab, which is processing in memory lab. So we're back, it's basically quite forward-looking, let's say. So I think it's good to learn using simulation. But processing in memory, what the lab you're doing, you could actually execute on a real machine, but you'll be using a simulator if that real machine is not available. So that's one use case of simulation. If real machine is not available, use a simulator to test your program, right? That's a use case that's not mentioned on these slides, but that's a good, valid use case also. So we're going to talk about simulating systems with especially a focus on memory, which is essentially what you're doing, but you'll have multi-core simulation also later. I also think about these as evaluating new ideas for new architectures. Basically, you have a new idea that's going to change the system. How do you evaluate this idea? Basically, the more, let's say, concrete question is, how do we assess how an idea will affect a target metric X? And X could be any metric, actually. X could be performance, energy, security, reliability. This will especially focus on performance energy, but there are also security. Think about those things. Basically, there are many metrics we design our systems for. Cost could be another thing. So there are, especially if you focus on performance, energy, and also security, I think there are a variety of evaluation methods that are available. You can theoretically prove things. That's nice. That would be nice. Usually, that's not easy to do in systems work, because systems work is very much dependent on the system and the workload changes, as we discussed. It's very difficult to prove things in what we do in general. Basically, we're very far away. If you want to prove things, you need to idealize some things and assume some things. And once you go into those assumptions become very limiting. As a result, the proof becomes very uninteresting, let's say. So workload-driven research and workload-driven work in general is very difficult to prove. You can do analytical modeling and estimation. You can build an analytical model, let's say an equation, and then you can basically say performance is, for example, a function of cache miss rate, and then the other cache miss rate, memory latency. You can basically have a linear model, for example. That could be an analytical model, right? And you get some information about the workload, plug the numbers to the model, and then estimate the execution time. That's one way of modeling. It's possible to do. It's actually good for very, very early design space exploration, or in limited cases where you know analytical modeling works really well. It's very difficult to do this at the full system level for sure, and also with many, many workloads executing at the same time. So this is also usually tough in architecture and systems. But there are some cases where you can actually do this. So this is not as difficult as theoretical proof, right? So simulation actually is the next one. And this is actually used very heavily whenever you change hardware, especially. And you do it at varying degrees of abstraction and accuracy, and we'll discuss this a lot. But then there are other methods, like prototyping with a real system. So now you actually build some hardware, do some prototyping, and get an idea of what your system would look like. Maybe not exactly in the way you envision, but based on some prototype that you build with some limitations that are not exactly resembling your envisioned hardware. And this is usually done with FPGAs today. FPGAs are very good, but you could prototype using other real systems also, potentially GPUs, for example, right? You could, you're envisioning some change, but GPUs may be a good way of capturing, let's say, 90% of the change, but not 10%. You do prototyping, and then you get some idea. Usually it's not perfect. Simulation can be much closer to, much more accurate, for example, depending on what kind of things that you're doing, that you're envisioning. And then real implementation. Clearly, real implementation is the best way to evaluate, or I should say, most accurate way to evaluate an idea. Real implementation means you implement a chip, for example, right? Assuming that's your goal. But you have an idea, you design a new memory controller, you implement the new memory controller, you roll out a new chip, and then you test it. Now you can get the metrics that you want perfectly accurately. But if you're exploring 10,000 ideas, this becomes completely unscalable, because you're not going to implement 10,000 different chips to pick one that's going to be useful, right? That kind of defeats the purpose. That's why this is not, basically, this is, in the end, this is your end goal, but this is not an evaluation method, if you will. Of course, you could do real implementation, depending on how you define implementation, right? This could be a register transfer level implementation, but even that's simulation, basically. So if you do an implementation in Verilog, that's not real implementation. This is real hardware implementation in the end. Does that make sense? Okay. So keep this in mind. Basically, whenever you have an idea, you could actually use all of these. But I think this is almost always gone. But other stuff is still remains. I think real implementation is almost always gone also. So these three things, analytical modeling, simulation, and prototyping, are important. So prototyping platform, we've actually seen an example prototyping platform. There are many, many examples, but I'll pick one that you have seen. This IEDM that was discussed earlier in processing using memory lectures by Juan. It's essentially a prototype that enables you to evaluate row clone and true random number generation, DRange style, as we discussed, using off-the-shelf DRAM chips, such that you can actually evaluate the performance benefits of this on a system. So this is actually a prototype. It's not a simulator, essentially. It gives you something that simulator can actually give you, like this is the end-to-end execution time on this workload. This is the improvement in micro benchmark performance, etc. So you can do a lot of things that you could do in a simulator, except for changing things very completely, as we will discuss. But this is a prototype, basically. And you've seen this also, so I'm not going to talk about this. Maybe we'll have a lecture, a more detailed lecture on this. But this is actually the first processing using DRAM prototype that's publicly available that we know of, and you can actually build on it. I think it's quite interesting. But this is one example of prototyping. What this does not enable is like ideal studies. So simulation is a bit more general in the sense that you can say, oh, I'm going to simulate things assuming a perfect branch predictor, assuming a perfect cache. I guess you could implement a simulation model on top of this that could enable it, but that's not prototyping alone anymore, right? So that's one of the beauties of simulation. This is still pretty bad. I think we should fix this next time. I don't know what's going on, frankly, but anyway, I don't expect you to read this, but it looks pretty bad for whatever reason. So, okay, so these are real results that you can get from a prototype, for example. It's a real micro benchmark you can run, and assuming the stuff that you implement in this prototype, this is the improvement of in-DRAM copy and initialization. And these are very good results. You can read the paper for more detail. And the paper discussed a lot of interesting things that you need to do in a real system. So the difficulty in prototyping is you need to essentially build a lot of things that you need to make the idea run on a real system. So this basically discusses alignment requirements of rows so that you can copy between them, allocation requirements. So it actually builds a memory allocator and memory mapper so that you can actually do in-DRAM copy and initialization nicely. It solves some of the problems basically, and plus coherence problems. So in a real prototype, you actually need to spend some effort to really get things working. Whereas in simulation, you can cut a lot of corners. You can say, okay, I'm not going to really implement this, but I know the result because I can execute the program on a real system, get the result, and assume some latency, right? You can actually do a lot of those things in simulation. So that's the beauty of simulation, basically. It gives you a lot more flexibility than a real prototype would. Okay, so I think the difficulty in architectural evaluation is, as I said earlier, the answer is usually workload dependent. Think caching, for example. Does caching work or not? It depends. Basically, the answer is depends. It's very much dependent on the workload. On one workload, you get 0% cache hit rate. On another workload, you get 100% cache hit rate in the steady state when things are warmed up. In pipelining, that's also true for pipelining. Basically, many things. Any idea we talked about, for example, the performance improvement of RAIDer is dependent on the how frequently you're accessing memory. That's true for SALP and different characteristics also, right? So workloads change, and system also has many design choices and parameters. So architect needs to design many ideas and many parameters for a given design. So you're implementing a chip that's going to be released 5 years down the road. It doesn't matter how many years, actually. It could be 6 months also. That's a very tight schedule, of course. You need to make many design decisions, basically. And you're changing a lot of things, many parameters. The question is, how do you decide what to change? And it's not easy to evaluate all possible combinations as well, unless you have a very good simulator. And clearly, you're not going to implement things like all of the possible combinations in hardware, right? And system parameters may also change, right? So basically, a lot of these things make architectural evaluation different. System parameters may change. For example, you run 2 workloads at the same time, 4 workloads at the same time, 6 workloads at the same time. You evaluate those things. You can change the multi-threading parameters. You can change the cache sizes, etc. So there are a lot of changes that you can do. So how do you explore this design space that for the chip that you're going to implement 5 years down the road, or the DRAM? It could be the DRAM chip, GPU chip, FPGA chip, CPU chip. All of those basically get affected by what I just described over here. So that's the difficulty. Clearly, you're not going to implement a different chip for every single potential combination, right? And that's where simulation comes in. And I think of this as the field of dreams, right? And it's very much like dreaming. But you need to be also constrained by reality a little bit. And this is where an architect comes in, actually. And simulation is a key tool of the architect in the end. An architect is a dreamer, a creator. Essentially, you're creating something that didn't exist, right? And as I said, simulation is a key tool in that it really allows the evaluation and understanding of non-existent systems, right? I mean, it could be processing in memory, right? Like we discussed. This doesn't exist, right? It could be processing in everywhere. This doesn't exist clearly today. How do you evaluate it? So simulation clearly enables the evaluation of these dreams, exploration of many dreams at the same time. It also enables a reality check of the dreams, but you may be thinking, oh, this is a great idea. But then simulation, assuming it's done right, can tell you, okay, it may not be that good, right? So it's a reality check. You can dream all you want, but you need to have a reality check at some point. It enables deciding which dream is better, which idea is better, basically. So that's good. So it basically gives you a comparison point, assuming you do things right again. But unfortunately, simulation also enables the ability to fool yourself with dreams if things are not right, if things are not done right. So if you forgot to model something really important, that's going to change basically which idea is better, then you have a problem clearly, right? You'll find out the hard way. Your processor may not perform as well, let's say. In the worst case, your processor is actually much worse than the processor you shipped 5 years ago. That sounds pretty bad. In the best case, maybe you're 5% better. But it also is not just you, it's the competitor, right? So basically, this ability to fool yourself is very dangerous. So that's why you need to really know what you're doing when you're simulating things. And also, you need to build confidence over time. It's not just, so how do you know what you're doing is right? This is where it's science as well as art at the same time. So experience plays a huge role in understanding and building simulators. So that's really important to think about. Okay, that's why you're gaining experience in building simulators or modifying simulators here. Any questions? Yes. Yeah, I think it depends, basically. It depends on the simulator, as we will see. There are many different goals in simulation. Some simulators, the goal is just design space exploration. You just want to get the high-level bits of relative comparisons and then explore some of the things in more detail. But sometimes your really goal is really accurate performance estimation. Then you need to design different simulator for that purpose. Yeah, you can validate things by doing other things like prototyping, based on some real hardware implementation. So you can basically have a loop that validates the simulation. Yeah. But that's a very good question, basically. We will see that in a little bit. So let me first tackle why do you want to do high-level simulation? So high-level simulation is essentially high-level language simulation, C simulation. You could actually design simulators in Python, etc., that abstract away what goes on in hardware, right? For example, you can say, if row buffer has the row I'm accessing, latency is equal to this, right? Clearly, that's not how hardware works, right? Hardware works. I mean, there's some construct that implements this, but those are gates, and those are some logic over here. So basically, you can have high-level language constructs to design a simulator. And the main issue with RTL simulation or low-level simulation which is done with Verilog, it's intractable for design space exploration. It's too time-consuming to design and evaluate if you have a simulator at the gate level, especially over a large number of workloads. Especially if you want to predict the performance of a good chunk of a workload on a particular design. That basically becomes intractable. It takes years, let's say. And especially if you want to consider many design choices. So you want something much faster. And there are many design choices, even if you look at a cache, right? Cache has many design choices. Memory control has many design choices, we will see. Processor core has many design choices. This is more in the processor core and many, many things, basically. Now, you can actually constrain yourself to something small, a memory controller, even that is actually intractable with RTL simulation. But normally we would like to consider even more things, right? Especially if you want to get an overview of the entire system. So the goal is really to explore design choices quickly to see their impact on the workloads that we're designing the platform for. And you always design a platform for workloads. Even general purpose processors are designed for workloads. Yes, they're general purpose workloads, but usually what happens in companies that are designing general purpose processors is they have a huge workload set and they run their ideas in simulation on that workload set. And hopefully they get good performance on average without destroying the performance of any single workload too much, let's say. So that's the general purpose design. If you're application specific, or like GPUs are relatively general purpose, but also relatively less general purpose than CPUs, so that's another set of workloads. If you're designing, I don't know, a machine learning accelerators, clearly you're constraining the workload space more. So you're always designing some workload space in the end. So there are different goals in simulation also. We're going to talk a lot about exploring the design space, but that's not the only goal. So the first goal, especially in research, also early in the design space, for example, you're going to ship a processor 5 years down the road. You're just exploring ideas right now. What should the architecture look like? This is the goal, basically. Explore the design space quickly to see what you want to implement. in a next generation platform, or proposed as the next big idea to advance the state of the art. So research and early design space exploration may have similarities. They quickly diverge from each other. In a company, when you do early design space exploration, you quickly want to decide things and move on to the next stage, let's say, so that you can start actually solidifying things. In research, you're not as constrained by what you're going to implement 5 years down the road. Maybe you don't care, right? In research, actually, some people should not care. 100 years later, maybe your idea will have impact, right? This is beyond the time scales of human life, let's say. Well, 100 years still is within the time scale of some humans' life, but 200 years, let's say, right? So in research, you may not care. Okay, so the goal is mainly to see the relative effects of design decisions. And this is important at the early stage in a company, as I said also. But then there's a complete different goal, which is matching the behavior of an existing system. Right? So you have an existing system. You want to match the behavior of it for multiple different purposes. Perhaps you want to debug and verify the system at cycle level accuracy. That could be one thing, right? And this may be easier to do in simulation. Maybe you don't have access to that platform, right, anymore. Or maybe you want to propose small tweaks to the design so that can make a difference in performance and energy. So an incremental change to the cache design. You cannot evaluate in hardware because the hardware doesn't allow that change. Otherwise, then you may not, you can actually put knobs in the hardware to evaluate such changes also, but assume that that's not done. Basically, you can actually, this is where you design a simulator that's very accurate, and then you modify it and see what happens. Here, the goal is very high accuracy, basically, because you really want to match the behaviors of an existing system. So you can see that these are actually two opposite things, and there could be other goals in between. For example, you have a very, let's say, high-level simulator that enables you to explore design space quickly, and then you build a lower-level simulator that's not still matching the behavior, but you want to do a little bit more design space exploration with focused ideas. So you already decided that you're going to design, 4 levels of cache, for example. Now you want to look at the cache policy. So you actually design a more focused simulator. So that's refining the explored design space without going into a full detailed cycle accurate design. You're still building there. Or gain confidence in your design decisions made by higher level design space exploration. So there could be other simulators that you built to gain confidence. Essentially, what happens in system design today is you start with a very high level simulation, and then you refine things with lower level simulators. And eventually you have a simulator that's at the gate level that hopefully matches the behavior of the next generation system. But you can actually inform that simulator based on the current generation system that you have also. So you can actually calibrate your simulators. And then once you actually implement the hardware, what you have is something golden, which is you have this very low level, you have all these simulation levels, simulators that you develop. You can calibrate all of them to the actual hardware, right? And the lowest level simulation, even the very log simulation, has some error compared to actual hardware. This is actually consistent. In many places, usually that error ranges from, 0% to 5%, sometimes even 10%, because what you do in Verilog is not exactly what's implemented in the chip, right? Because there's a translation process over there also. People do layouts, custom tools may not exactly translate what you envision. There are some critical paths that people break later because they find out that, okay, there's a problem over here. Let's break this critical path. Now your simulator may not be informed. So the people who designed the RTL do not know about that happening. As a result, your Verilog simulator, which is assumed to be very accurate, diverges from the real hardware implementation. And how do you calibrate it? Well, you know the result of the real hardware implementation. You do essentially this. You match the behavior of the existing system and basically change your simulator, figure out where it's wrong, and make it match the behavior exactly. So that's how it works, basically. It's essentially a feedback loop. You can actually calibrate all of your simulations based on this. Usually, as you go higher in the hierarchy, the simulators have more error, of course. But again, you may not care about that error as long as you get the relatives right, relative comparisons right. Any questions? Okay. In research, this is done also that way, but in general, the goal of research is not this, unless you have an agenda in research saying that, I want to develop new ideas in debugging, for example, right? So it depends on what kind of research you're doing. Okay, so in simulation, there are many trade-offs, actually. There are 3 metrics, maybe 3+1, to evaluate the simulator. One is speed. How fast can the simulator simulate a program, let's say, or whatever it is that you're trying to simulate? How flexible it is, and how accurate it is. There's also simulation time. I don't want to include it here, but that's also important, let's say. That actually has interactions with all of these. No, simulation time, not simulator development time, I should say. That has interactions with all of these. So speed is how fast the simulation runs. It has some metrics, basically. Slowdown compared to the real system is one example. How many instructions per second can you simulate? How many cycles per second you can simulate? Different metrics have different upsides and downsides depending on what you're looking at. But basically, this is the speed of the simulator. Ideally, the faster, the better. Regardless of what you're doing, the faster, the better, because that could make you get you to decisions much more quickly, right? Doesn't matter which level of the simulator. The faster, the better. Okay, well, assuming everything else is constant, of course, right? The faster is not better if you're getting rid of a lot of accuracy and your goal is this, clearly, right? And then flexibility is how quickly can one modify the simulator to evaluate different algorithms and design choices. Clearly, ideally, you want a flexible simulator, especially when your goal is to explore the design space, right? That enables you to change the simulator very quickly. And then there's accuracy, which is how accurate are the performance and energy numbers the simulator generates versus a real design. This is simulation error, essentially. And you can quantify this. Assuming you have a real design, you can quantify it. You can guess it, assuming you don't have a real design. But basically, these three, usually these three form, let's say, a triangle, and usually you can optimize two of them very well at the expense of the other. It's very difficult to optimize for all three at the same time. I didn't want to include the fourth one, which is simulator design time, but that's also important depending on your situation. Essentially, the relative importance of these metrics varies, depends on where you are in the design process and what your goal is. So the previous slide, the goal, where you are in the design process, really determines how much, let's say, inaccuracy you can tolerate and how much slowness you can actually tolerate. If you're doing early design space exploration, you're okay with being fast but less accurate. So fast, speed, and flexibility are much more important in early design space exploration compared to accuracy. Again, you can define accuracy in multiple ways also, right? This definition of accuracy is very strict. But the other definition of accuracy, how much do I get my design choices right? If the simulator tells me you will get, let's say, 30% improvement compared to if you implement out-of-order execution versus in-order execution, what is the error on that? If I make a 30% error, maybe that's not good, right? Then you get 0% performance improvement. So basically, there's some tolerable level over there. Unfortunately, it's not as much of a science here. It's more of an art today, because you normally go to the next level, and then you may figure out that you're wrong in the next level, and then you try to basically optimize. Basically, this levels of simulation actually enables you to figure out what's wrong at the higher level as also potentially. Okay, so you can trade off these things. As I said, speed and flexibility affect how quickly you can make design trade-offs and decisions. Accuracy affects how good your design trade-offs or decisions might end up being. And also it affects how fast you can build your simulator. So simulator design time is especially a strong function of accuracy. The more accurate you want to be, the more perfect you want to model a real system, the longer time you're going to spend designing the simulator, because there are many, many things that happen in a real system that you have to model essentially. So if you want 100% accuracy with no error, essentially you have to consider everything that happens in a real system, right? This may depend on your workload, of course, but I'm assuming a complicated enough workload that exercises stuff in a real system. Flexibility also affects how much human effort you need to spend modifying the simulator. So that's also important, right? That's another simulator modification time, basically. So there are other metrics. I don't want to necessarily call them secondary metrics, because they could be primary if they're on your critical path, but that's also important. So if you have a very terrible simulator that no one in your company knows how to modify, you may not be making much progress, right? Okay, so as I said, you can trade off between these three metrics to achieve design exploration, design space exploration, and decision goals. And your goal is dependent on what you're really trying to do. So the key idea in high-level simulation is to raise the abstraction level of modeling to give up some accuracy to enable speed and flexibility, and to enable quick simulator design. That's the idea, basically. That's what we do as architects. We start with high-level simulation. Of course, we can go all the way down to low level, but that's what you start with, high-level simulation. The key advantage, of course, this also has advantages and disadvantages. You can hopefully still make the right trade-offs and can do it quickly, ideally. All you need is the modeling of the key high-level factors. You can omit corner case conditions as long as they're not really affecting things. So this is where you need to be careful, experienced, and have good judgment in a sense. And also experience helps modifying the simulator. What is the corner case, right? How can you tolerate that corner case? Can you tolerate it? These are good questions, basically. So you can omit some things, basically. That's the idea. All you need is to get the relative trends accurately, not the exact performance numbers over here, because that's the goal, basically. Yeah. Yeah, I mean, for example, I'll give you an example. Maybe this is not a great example of omitting things, but there used to be simulators in the architecture community that used to model memory like this. I guess cycles plus equals memory latency. And memory latency is a constant. That's one way of modeling DRAM, right? You got rid of everything that we've discussed in DRAM. You basically got rid of bandwidth constraints also. Well, it kind of looks, it's not exactly that way, but basically you increment the cycles with the memory latency. That's when your request gets serviced. That's one way of abstracting. You omit lots of corner cases there. Row buffer gone, banks gone, channels gone. Everything is gone in the memory system. It's just incrementing cycles. Maybe you take into account bandwidth. So is that okay? Is that not okay? Well, it's okay if DRAM is not the bottleneck in your workload, which we know is not the case in most workloads, but there are workloads that happen. So you need to know basically when it's okay and when it's not okay to do things. Okay, so that's an example. That's an extreme example. That's an example, right? Or another example is you can assume every instruction takes the same latency, right? And you can assume a constant IPC, no dependencies, etc., and model processor performance that way. If your performance is not bottlenecked by the processor, maybe that's okay again, right? So depends on what you're investigating also. So disadvantage over here is clearly it opens up the possibility of potentially wrong decisions. If you omit the wrong things, or if you don't model some things as they should be a little bit more carefully modeled, then you can actually now get into potentially wrong decisions. For example, if you say if you don't model lots of stuff in your memory and your workload is extremely memory bound and is affected by all of these things that we've talked about in the memory in the DRAM, then you're probably going to make a lot of wrong decisions if your simulator doesn't model things. So basically, the key question is how do you ensure you get the relative trends accurately? This is where, again, a lot of experience building simulators helps. So simulation is actually progressive refinement. I already said this earlier. You basically start with high-level models, build medium-level models, low-level models, and then real design. And the answer to the previous question is you gain experience through this refinement so that you go back from the real design and fix all of these simulators just enough so that you satisfy the goals that are there at each of the levels. That's the idea. So once you have a real design, you have something really golden to enhance everything that you have done so far. And if you have many, many real designs in the past, like if you're a big chip company who has designed hundreds of chips, then you actually have a lot of experience and actually fix a lot of the models nicely. I'm not saying it's always done, but you have the potential to do this, basically. And people do it to some extent, certainly. There are actually people in these big chip design companies whose sole task is getting the low-level models match the real design. That's not easy, basically. Even that is a lot of work. And you need to be a very rigorous, methodical, meticulous person to be able to do that. Yeah. Okay. So as you refine, meaning go down the above list from top to bottom, abstraction level clearly reduces, right? Accuracy hopefully increases. Not necessarily if you're not careful, of course, right? You can make a critical error in this model that is not present in this model. So your accuracy is actually worse. That can happen. But usually it increases if you're doing the right things correctly, let's say, if you're careful. Flexibility reduces. Flexibility is actually much lower as you go over here. Speed likely reduced again, unless you go to real design, of course. Real design is not a simulator, but real design is much faster than everything over here. But it may not enable you the things that the simulator enables you to do, of course. Right? And as I said, you can loop back and fix higher level models, right? And then you can iterate over years across many real designs. So I think a good architect is really comfortable at all levels of this refinement, whatever we discussed over here, hopefully even in a real design, including the extremes. And you need to know when to use what types of simulation. That's important. If you have an idea, how do you evaluate that idea, basically? Assume that you decide on a simulation to begin with. In fact, I would actually add high-level models, abstract C. There should be analytical modeling that could actually feed the high-level models also over there. So there's a connection between analytical modeling and simulation also. You can go back and fix the analytical model also. So there's also another thing over there that I didn't really include because we're talking about simulation. But basically, you need to know when to use analytical modeling, simulation, etc. What is good enough to demonstrate the idea, depending on your goal, right? So that's really important. As I said, what type of evaluation method? And recall that there are many evaluation methods available. Okay, any questions? Is this interesting? Yeah. This actually applies to any simulation, not just architectural simulation, but we're focusing on architectural simulation. If you have time, I'm going to talk about something totally different. But any simulation that you do has similar characteristics. But let's talk about some interesting things in architectural simulation. This is actually a very broad area. There is a lot of work in this area. I think some of the things are still not extremely well understood, but let's talk about some things, let's say. So as I said, the goal of simulation dictates many things. It drives many design choices and what simulator do you build or even use. Because as an architect, you may not want to build everything from scratch, right? There may be many simulators available. What do you use? How do you combine them, etc.? And again, the goal of simulation dictates the trade-off that you make between accuracy, flexibility, speed, design time of the simulator. And there could be many possible goals, as discussed earlier. We discussed some of those goals. But even if you focus on some goal, your goal may be entire system performance estimation, or you maybe want to focus on some components, right? Just the cache, just the SSD, just the memory. So you may actually want to look at just the components. Or another goal could be just profiling for statistics, right? You may not want to estimate execution time, but you may just want to profile how much cache misses you will get, right? So this is a different kind of goal in the end. So there could be many goals, right? You can imagine many things. And in general, you can divide this into what, how, where, when, kind of loosely. What do you simulate? Do you simulate a component or components, a collection of components, or the full system? Full system simulation is usually very hard, but they exist because you can cut corners. Do you simulate programs like binaries, or do you simulate traces? Meaning traces are basically execution traces, instructions that are executed, you recorded them somehow, and you're going to replay them in the simulator. And we're going to see some differences over there. How do you simulate it? Many choices over here. Do you simulate in a functional manner? If your goal is not timing, if your goal is just debugging a program, for example, in a system, functional may be enough. This is functionality, essentially. But timing complicates things. Do you design the simulator as an event-driven simulator or cycle-by-cycle polling simulator? I don't want to go into a lot of simulator design details, but there are trade-offs over here in software engineering, clearly. How do you do the state maintenance and recovery? There are many, many things, basically, in simulation design. And then there's another interesting question. Where do you simulate things, right? Each thing that you want to simulate. Do you simulate in software? Where does the software run? Do you do it on a CPU, on a GPU? Or do you accelerate things in hardware? People have been looking at FPGA accelerated simulators, for example, so that you can do part of the simulation in FPGA so that you can actually do things much, much faster. And these are actually used in some places. And then when do you do things in simulation? That's, again, interesting thing, because simulation, you can do a lot of things. You can get Oracle information, meaning you can say, okay, I know where this branch is going to go, and I'm going to model a perfect branch predictor, right? So you can actually see the performance improvement a perfect branch predictor, a perfect cache provides. A zero latency DRAM provides using simulation, right? Or do you execute like a real machine, right? So basically, you can actually go into a lot of these things, but we will not be able to have time for it. But I think inputs and outputs kind of give you a good idea. So what's the input to your simulator and what are the outputs? So again, inputs can be multiple things, but it could be a program binary. It could be a trace. It could be multiple program binaries or multiple traces. Or this is now you're thinking of just a program, right? A trace is actually a particular execution of a program. It's not the binary. It's just these are the instructions that you need to go through. Binary is binary. You just need to simulate as if a machine is going to operate, right? So this is the difference between a binary and a trace, right? But then program, you're not really, a system is not just a program, right? It's really the system state. So program binary is something that sits in memory. You could actually have a system image that could be your, that could be the input to your simulator, which is not the input in your simulators that you're working on in your labs. This is a more complicated simulator. What you're given is a system checkpoint that essentially has, okay, I take a checkpoint in my system right now that's running PowerPoint, Zoom, etc. Hopefully it's running Zoom. Okay, it's running Zoom still. It's live streaming. So it has a memory checkpoint. It has the checkpoint of the CPU. It has a checkpoint of the SSD. It has a checkpoint of the network. So basically it has everything. That's my checkpoint. That's my starting point. And I'm going to simulate from there. That's your full system right now, right? So that's a very different type of simulation that you're doing right now. This is the full system aspect, and it becomes much more complicated to model things clearly, especially if you want to do it at very high accuracy. And imagine that this could extend to a distributed system, right? What is the system checkpoint if you have a distributed system, if you want to simulate a data center? So it becomes interesting, basically. And people have built data center simulators also. But we're going to constrain ourselves to single node, let's say. So outputs could be different things also. It could be functional outputs. It could be the results of the program. Statistics about functional execution. How many adds do you have? How many multiplies do you have? Basically, these are functional things. Usually, functional simulators are also called emulators. There's a slight difference between emulation and simulation. Functional simulators, people, I think, sometimes call them emulators. It's really emulating what the processor would do at a functional level. Timing now becomes interesting because here you can get the execution time of each program. That could be the output. System throughput of all programs, energy consumption, statistics about timing and performance events, maybe even reliability, etc. Basically, that becomes a little bit not timing related, but I consider it timing related. That's not essentially functional, perhaps. But basically, timing related makes things harder. But there is this dichotomy between functional and timing. And if you want to build a timing simulator, you normally build both of these, functional and timing. Okay, we're going to talk about that. Any questions? Okay, so functional versus timing. Let's talk about that. There are many issues actually, but I think I kind of alluded to it. The purpose is what do you need and when? When do you want to use a functional simulator? If you want to, for example, debug a program on a future system, that's where functional simulation may be okay, right? Debug the instruction mix, if you want to minimize some sort of instructions in your program, functional simulation may be enough. But if you want to predict the execution time, then you have to include some timing components. And if you want to get execution times, then you need to normally integrate functional and timing simulation, especially if you have an execution-driven simulator. We're going to talk about that also. Let me cover these relatively quickly, and then we'll talk about this functional and timing a little bit more, because this is interesting. People have designed different types of simulators. Full system versus component level. Like, again, this depends on your purpose. If your goal is to optimize an SSD without considering anything else, an SSD simulator may be good enough. If your goal is to optimize DRAM without considering anything else, a DRAM simulator may be good enough. Then you're making the trade-off, saying that I'm going to optimize this component, ignoring everything else. Right? That's the trade-off. If you're fine with that trade-off, then do component simulation. CPU is a component also, right? That's where full system comes in. Full system basically is what I just said earlier. It models everything. Then the question becomes, what should be modeled at what level? Granularity, operating system, virtual machines, memory allocator. So there's a lot of stuff that needs to be modeled if you want to model a full system, right? That's why CPU simulators are easier, but still they're not easy, I would say. They're easier. And then also another question is, what do you simulate, right? Do you simulate a complete workload? So what is the workload, first of all? Is it a single program? Is it multiple programs? Meaning, what is a complete workload? Like a complete workload, you give input and you may get the output after, I don't know, 10 seconds. Usually those workloads exist, but they're not the common case, right? In simulation, that 10 seconds become can get amplified. Well, if it's a timing-based simulator, for example, you may get 1,000x slowdown. Right? That 10 seconds becomes 10 times 1,000 seconds, depending on the simulator that you've designed. Right? So complete workload simulation is actually usually out of the question, because 10 seconds, okay, that's maybe an interesting workload. What if the workload runs 2 days? 2 days times 1,000 timing, good luck. 2,000 days, right? That's 5 years, basically, just to give the perspective, right? So that doesn't sound good, basically. So normally, complete workload simulation, people don't do it. People usually simulate a number of instructions, or you do more rigorous, statistically rigorous techniques like sampling-based simulation. You figure out what parts of a program are hot, given an input, and you focus on that. That's one sort of sampling. Figure out, for example, people try to, there are some works that proposed profiling the program, figuring out what functions are hot and simulating only those parts. Of course, you need to be careful, right? Because there may be interactions between different functions. Or some people have proposed actually pure sampling-based simulation. Don't worry about what's hot or not. Just sample at some rate. So basically, fast forward in the program and then simulate 10,000 instructions. And then fast forward, maybe 1 billion instructions, simulate 10,000. So people have actually looked at the accuracy, etc., characteristics of this sort of simulation. There's no basically perfect way of doing this, let's say. So this is where workload dependence actually kills you, let's say. Okay. And then there's another issue, which is an important issue, basically. It's related to this one actually also, because it especially happens with sampling-based simulation in the second type of sampling. If you fast forward 1 billion instructions and simulate 10,000, what happens to state? Because in a simulated system, you have a lot of state, caches, branch predictor tables, memory, etc. How do you simulate those? Do you assume they're empty, cold, or do you assume some steady state behavior? If it's steady state behavior, what is the steady state? Meaning how warmed up they are. So this is actually a bit also difficult, but people try to warm up the structures in general because cold start, you may actually get cold start effects that are not realistic, right? So when a program just starts execution, you need to populate the caches. If a program has locality, then you're basically, if you're modeling just the cold start part of the program, you're just modeling something that doesn't happen in the steady state. Assuming the program runs much longer than the cold start time, you really want to model the steady state, basically. And the steady state is when the caches are warmed up, meaning the locality is there in the caches and you're exploiting it. So there's a lot of actually theory over there and also statistics. So simulation actually is very much combined with statistical modeling. And if you know statistics really well, this actually helps you to do very good simulation. Well, let's say very good high fidelity simulation, let's say. I'm not saying accurate simulation completely, high fidelity simulation based on the accuracy trade-offs that you have made, right? Okay, so this is very interesting, I think. Any questions? Okay, let's talk about functional and timing. This is interesting. This is an old example. Simple Scaler was a simulator that was used for some time in architecture. That was one of the first open source simulators in architecture. It also modeled memory with the cycles plus equals memory latency. So it actually led to a lot of bad decisions, let's say, and bad papers because of that bad modeling. That's not necessarily the fault of the people who designed the simulator, I would say. There's a simulator designer, there's a simulator user. As a user, you should be careful what you do with the simulator, right? You cannot say, oh, I have this idea, let me test it. Oh, it gives great results. Let me write a paper. No, that's not how it works, right? The way it should work is, okay, I have this idea, let me model it accurately in the simulator. And then if the results look good, let me analyze them and figure out why the results are good. So basically, you need to do due diligence as a user to the simulator. It cannot be just, oh, I don't understand how the simulator works. Let me input and get output and then call the day. Unfortunately, that happens also, and that's not a good thing, basically. So basically, it's really important to understand the simulator that you're dealing with. Otherwise, you can produce garbage very easily with this, right? Because it's very prone to garbage also, as you can see, right, as we have discussed. So basically, this is an example of functional. For example, you can see that there's a fast simulator that's only 420 lines of code, no timing, and it can, this is old stuff, 4+ millions of instructions per second. So it can have a very fast timing, non-timing functional simulator. There's another simulator over here with some checking, etc. But basically, you can see that simulators can get complicated. Even functional simulators can get complex. Here, you basically have a cache model, and you can get cache statistics. Still no timing. Here, it's an out-of-order processor simulator, and it has timing with some simplistic assumptions, basically. It's only 4,000 lines of code. That's the beauty of the simulator. It's very simple. That's why it's called Simple Scaler. but it may not be very accurate. So functional versus timing is very interesting because there are different ways of combining them. If you want to do timing simulation, you normally need to do some functional simulation because functional simulation is needed so that you know what instructions get executed, right? I'm assuming an execution-driven simulator here, which I'm going to define later, but basically you get an instruction, you need to understand what that instruction does and model timing accordingly. So for example, if the instruction is a load, if the instruction is an add, you model the dependencies, and if the instruction is ready to execute, you basically figure out when that instruction can execute and when its result is available, and then you basically execute the next instruction that comes after that. If it's a load, you model the cache hierarchy access and timing based on that. So you can develop a simulator that doesn't decouple timing and functionality. You can basically have a single monolithic simulator that models everything as much as possible at the same time. But this is usually not good practice to design simulators, because these are two distinct tasks that you can actually take advantage of to simplify the design of the simulator. So people have done functional first simulation. This is actually very commonly done. This paper over here that I borrowed this figure from actually is proposing a timing first simulator. I'm not going to go into the details exactly, but functional first means that you have a functional simulator that executes the program functionally. Basically, you model an ISA, you figure out the result of an add instruction, and then you feed that information. So you have all the knowledge at the beginning of the simulation. Let's say at the beginning, if you look over here, the first thing you take is a binary. You take the first instruction, you execute it, you figure out what it does, and then you basically send some information to the timing simulator, and the timing simulator models it. Basically, it models the iCache, it models the queues in the pipeline, it models the out of order engine. Basically, it simulates everything that happens out of order except the execution of the instruction. Make sense? And basically, it keeps feeding information that it finds. And now in the functional simulator, you can make choices, right? What instructions do you send? You can model a branch predictor over here in the functional simulator also. That branch predictor drives what instructions get sent to the timing. Now things become a little bit interesting if there needs to be feedback over here, right? The feedback happens when the stuff that's what happens in timing requires you to change what gets executed, like the program counter, for example. So that becomes interesting, I think. So that's something that happens, especially when you're simulating multiple threads, for example. Your functional, you may not actually predict which function should it get executed first, because you're simulating multiple threads, and one thread gets the lock, the other thread doesn't get the lock. But you kind of assume that, or you assume something, or you need to stall your functional simulator until you know that information, basically. So there needs to be some feedback from the timing simulator to the functional simulator to model things accurately, right? Because multiple threads communicate, and you cannot determine everything at the functional level, because communication, who gets the lock, is dependent on the timing, for example. So that's one very good example of that communication. So usually you have something like this. There's some feedback. Now, another benefit of functional first simulation is you basically can say, oh, I have a perfect branch predictor. I'm assuming everything is predicted perfectly and derive the timing based on that. And that's the execution time I get. And then you can compare it to a non-perfect branch predictor and see the headroom, right? If you want to do perfect caches, again, you could potentially do it in the function, assuming some timing, right? So basically, you can play a lot of tricks if you do functional first. Now, timing first is also interesting, but I'm not going to go into that. You can actually take both, meaning you can actually have another functional simulator that checks correctness of what you do in the timing. Basically, you can get complex in this one, but I don't have time to cover all of these. Any questions? I don't want to go into a whole lot of guts in the simulator design, but this is an example, functional first model. This work proposes that timing model is in the FPGA, functional model is not the FPGA, but you can see that it's doing essentially what we kind of discussed. You send instructions over here, there's a timing model, and then timing model provides feedback. And feedback could be, oh, you've done the wrong thing, meaning this thread got the lock and this other thread didn't get lock. So roll back the thread that is not supposed to get the lock. There are some things that you don't know here because they're dependent on the timing. Okay, so there are other issues. I kind of discussed functional timing, but validation of accuracy is important. How do you validate functional accuracy versus timing accuracy? Functional accuracy is usually easier because it's the specification, right? Functional accuracy is specification of a system, instruction set architecture. Assuming that you have a golden model for the ISA, hopefully you get the functional accuracy right. How do you do the validation? Do you do it online versus offline? So there are many questions over here that we don't have really time to go into. But simulation acceleration is also important. As I said, speed is important, right? I gave you an example. You don't want to wait 5 years for a simulator result for a given configuration. So hardware support is actually, some people have explored that. Software methods clearly help things like memorization. Careful software, actually, better software engineering in general is a good idea. In fact, computer architects, if you're a really good computer architect, you should also be a very good software engineer. This is, I believe it's very equivalent. Because you need to simulate things really well, and if you want to simulate things really well, you need to be a really good software engineer as well. Trace-driven and execution-driven. I think I've covered this a little bit, but trace-driven means you captured a trace somehow. It's a particular form of execution, basically a particular, let's say this instruction comes after this instruction, etc., and some results, and it drives what's modeled in simulation. You don't basically take a program and execute that program to determine what to do. So where does this make a difference? So trace driven, you may capture the trace using some functional model, or you can capture the trace using real program and have a dynamic trace of instructions. Now, if you want to model something that is not in the trace, for example, if you're the simulator that you're modeling has a branch that's mispredicted and you don't know what needs to be executed in the mispredicted path because it's not in the trace, some things become inaccurate. Or the captured trace is based on some particular lock ordering, lock acquire ordering in a multi-thread environment, for example. Again, if that lock ordering changes, the scheduling changes in the threads, then you may not actually accurately model things. So trace-driven in general is less accurate. People have tried to fix this because it's easier, if you will, but it's very difficult to completely fix. Whereas execution-driven simulator itself emulates the program execution and determines what is executed and drives the timing based on that. So basically, it affects what can be modeled. A lot of the interesting simulators are execution-driven, but trace-driven has its value also. No question about that. And again, you can apply this concept to components also. So I'm talking about CPU as a component, but you can apply it to DRAM, for example. These are the traces of requests that I assume I will get from the program, and then you can reorder based on that. Or you can model the program and feed actually what you expect, what is going to really happen, assuming you accurately model into the DRAM simulator. Okay, so there are a lot of interesting things. I will probably not talk about these, but do you do the execution only in the functional simulator, or also in the timing simulator as well? This is an interesting thing, basically. Execution means basically you execute the instruction, figure out what the result is. In the front end, in the functional simulator, this is good to do because you validate the functional simulation and then drive the timing. But why should you ever execute in the timing simulator? Basically, you repeat the execution. This may be interesting because there's some timing dependent execution. For example, if you want to value predict the L2 misses, you really want to inject the result of the value predictor at that point in time into the result of the instruction, right? So if you're trying to predict, for example, an instruction, a load is loading into register 2, and the value, the actual functional, assuming you do functional first simulation, that's what execute at front end means. You do functional first simulation. In the functional first simulation, you cannot get the value predictor captured because the value predictor state is dependent on the timing of the instructions, how different instructions have updated. So you've executed things accurately over here. You assume that R2 is, for example, 50. But in timing, you figure out that the value predictor predicts that value to be 5. Right? Now your execution and timing or functional and timing simulators diverge. And that's a problem, clearly, because what comes next should really have gotten the value of 5. Right? So this is where things become complicated. Modeling things like value prediction, or as I said earlier, lock ordering, thread ordering becomes difficult because these are very timing dependent events. That's essentially why you really need to have good state maintenance and recovery mechanisms. So you need to inject this value somehow to the functional simulator and replay the instructions that have happened so far. Or you can go crazy you can actually try to predict the value in the functional simulator as if it would happen in the timing simulator. And most of the time you're accurate, then you don't need to do this as much. But there will be some cases where you're not accurate because there's some divergence. Because in the functional simulator, if you think about functional simulator, it's an oracle, right? You can think of it as the oracle. This is how the program is executed. You can steer that oracle in the wrong path if you want, as long as you checkpoint and you can recover. But you can basically try to reduce the overheads of what you do in the timing simulator also. So simulator design actually opens up a lot of interesting possibilities. Right? So state maintenance and recovery, this is important because you need to, for example, if you're an execution-driven simulator, you need to execute on the wrong path. So you need to drive this functional simulator to the wrong path. How do you do that? Again, this could potentially be dependent on the timing. You need to drive the execution-driven functional simulator with the wrong value, for example. And then you'll need to be able to eventually recover. So you need to actually do checkpoints. That's why these papers over here have checkpoint and rollback engines. So you can actually checkpoint and roll back the functional simulator. Okay, and then there's the other issue. Now we're going into more software engineering, but event-driven versus cycle-by-cycle polling. This is one of many simulator design choices. Event-driven means basically you have an event queue and you fast forward the time to the first thing that's interesting in that event queue, as opposed to modeling every single cycle, right? So clearly cycle by cycle has downsides. Event-driven is more complicated design though. Okay, any questions? I've covered a lot of simulator design stuff. Yeah. So that's a good question. So you can model the functional aspects of memory controller. Yes, certainly. Like, does it obey the DRAM standard, right? Because there's some specification, and you model your simulator in a functional way such that it perfectly matches the specification without any timing information, right? You ignore all the timings. You just look at the functional aspects. Yeah, you can do that, certainly. You can do that with anything as long as it matches the specification. But DRAM control is a bit interesting because the specification includes timing in that particular case, yeah. So I would say that's a bit harder to do. Mm-hmm. Yeah, if your functional specification includes timing, as is the case in many DRAM systems, then yeah, you will need to have something that combines both. Like purely functional simulation is nice in cases where your specification is independent of timing, right? Which is ISA, for example, instruction set architecture, or operating system. This is how the page tables, updates, etc., should behave, right? There's no timing included in any of the specifications. In DRAM, it's a bit special. Okay. I think we've covered a lot and we've exhausted the time. So if there are no burning questions, we will start here in the next lecture, which is tomorrow, and hopefully we'll go into emerging technologies. Okay, take care. I'll see you tomorrow.
Is it your job now?
Yeah.
You take this course, you'll have many ideas for them. Let's talk about it.